Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're setting out on a journey toward one of the strangest endings the universe has ever imagined. Not the death of a star, not the collapse of a galaxy, not even the fading of the cosmos itself. Instead, we're going to explore the fate of an object so powerful that for decades scientists believed it might outlive almost everything else in existence. A black hole. If you've ever seen an illustration of a black hole, you've probably noticed how permanent it looks. A dark sphere surrounded by a glowing ring, sitting silently in space like some cosmic drain from which nothing can escape. Light falls in, matter falls in, entire stars can disappear into one. Once something crosses the boundary known as the event horizon, it never comes back, or so it seems. Yet modern physics has revealed something astonishing. Despite their reputation as the ultimate cosmic prisons, black holes are not immortal. They do not last forever. Given enough time, even the largest black holes in the universe will eventually disappear. And when I say enough time, I don't mean millions of years. I don't mean billions of years. I don't even mean trillions of years. The death of a black hole unfolds across timescales so vast that ordinary numbers begin to lose their meaning. We're talking about stretches of time that make the entire history of Earth seem shorter than the blink of an eye. Periods so enormous that all human civilization, every pyramid, every city, every book, every memory of our species would occupy only the tiniest fraction of the story. Somewhere out there, deep in the future, black holes are dying incredibly slowly. Tonight, we're going to find out how. Before we begin though, I'd love to ask you something. Where are you listening from tonight? Are you tucked into bed beneath a warm blanket? Relaxing on a sofa after a long day? Perhaps you're listening while watching the rain against a window or looking up at a clear night sky. And while you're settling in, here's another fitting question. What time is it where you are right now? It's a funny thing to ask at the beginning of a story about black holes. After all, we're so used to measuring time in minutes, hours and years. We glance at clocks, we check calendars, we count birthdays. But over the next little while, we'll be dealing with timescales so enormous that even entire civilizations begin to look like brief flashes. If you find this journey soothing, interesting, or simply a pleasant way to unwind, I'd be very grateful if you'd consider liking the video and subscribing. It helps this quiet corner of science reach more curious minds who might enjoy drifting off among the stars. Now, get comfortable, let your thoughts slow down, and let's begin with a surprisingly simple question. What does it actually mean for something to die? For most things in our everyday lives, the answer seems obvious. A candle burns out, a battery runs out of charge, a car eventually stops working, a tree grows old and falls. Death usually implies an ending, a point where something can no longer continue doing what it was built to do. Stars fit this definition quite nicely. Stars are essentially giant nuclear furnaces. Deep inside their cores, hydrogen atoms fuse together, releasing tremendous amounts of energy. That energy pushes outward while gravity pulls inward. As long as the balance holds, the star survives. But eventually the fuel runs low. The star changes. Some become white dwarfs, some become neutron stars. The most massive stars collapse into black holes. In each case, we can identify a process. A source of energy runs out. A transformation occurs. The object enters a new state. Black holes seem different. Unlike stars, black holes aren't powered by nuclear fusion. They don't burn fuel. They don't generate light through ordinary processes. In fact, a black hole appears to be the very definition of permanence. Imagine tossing objects into one. A rock falls in, then another, then a mountain, then an entire planet. The black hole simply grows. Feed it more matter and it becomes larger. Feed it more energy and it becomes larger. Everything seems to add to its existence rather than subtract from it. For a long time, this led scientists to a remarkable conclusion. Black holes might live forever. The reasoning appeared perfectly sensible. If nothing can escape a black hole, then how could it ever lose anything? A bank account only shrinks when money leaves. A lake only empties when water flows out. A star only dies because it radiates energy into space. But a black hole, nothing comes back out. At least that's what physicists originally believed. The event horizon, the invisible boundary surrounding a black hole, seemed absolute. Cross it and escape becomes impossible. Not difficult, not unlikely, impossible. Even light, the fastest thing in the universe, cannot get away. And if light cannot escape, what hope does anything else have? So for decades, black holes occupied a rather special place in science. They were cosmic endpoints, final destinations, the ultimate one-way journey. A star could die and become a black hole, but a black hole itself appeared incapable of dying. The story simply stopped there. Then something unexpected happened. Physics, as it often does, started asking uncomfortable questions. One question proved especially troublesome. What happens near the edge of a black hole? Notice that I didn't say inside the black hole. That's important. The mystery began at the boundary itself, the event horizon. To understand why, let's briefly imagine space not as empty nothingness, but as something far stranger. Modern quantum physics suggests that what we call empty space isn't truly empty. Even a perfect vacuum is surprisingly busy. Tiny quantum fluctuations constantly appear and disappear. Particles emerge, particles vanish, energy flickers in and out of existence. The vacuum of space is more like a restless ocean than a perfectly still pond. Most of the time, these microscopic events happen so quickly that they barely matter. The universe carries on without noticing. But near a black hole, things become interesting. Very interesting. Picture the event horizon as the edge of a waterfall. Now imagine tiny pairs of particles appearing right beside that edge. Normally the pair would appear and disappear together. No lasting effect, nothing unusual. But near the event horizon, the black hole's immense gravity can separate them. One particle falls inward, the other escapes. Suddenly, something that should have vanished remains behind. To a distant observer, it looks as though the black hole is emitting particles, not swallowing, emitting, and that's a deeply strange idea. After all, black holes are supposed to be the objects from which nothing escapes. Yet here was a prediction suggesting that black holes might slowly leak energy into the universe. The physicist who developed this insight was Stephen Hawking. In the 1970s, he combined ideas from quantum mechanics and black hole physics to reach a conclusion that shocked the scientific world. Black holes are not entirely black. They're not completely silent. They're not perfectly eternal. Instead, they glow, very faintly, very slowly, but they glow. Today we call this process Hawking radiation, and it completely changed our understanding of black holes. Before Hawking's work, black holes looked immortal. Afterward, they suddenly had an expiration date, an extraordinarily distant expiration date certainly, but an expiration date nonetheless. At first glance, this may not sound dramatic. After all, lots of things emit radiation. Your body emits radiation, the Earth emits radiation. Even a warm cup of tea emits radiation. But Hawking radiation carries a profound implication. Energy leaving the black hole means the black hole loses mass, and losing mass means shrinking, very slowly, almost unimaginably slowly, but shrinking nonetheless. It's a little like discovering that a mountain is losing a single grain of sand every century. At first, the change seems meaningless. The mountain still appears permanent, stable, unchanging. Yet if you wait long enough, the story becomes very different. A black hole that emits Hawking radiation gradually loses energy. As energy leaves, mass decreases. As mass decreases, the black hole becomes smaller. And once it becomes smaller, something even stranger happens. It begins emitting radiation faster. This creates a remarkable feedback loop. The smaller the black hole becomes, the faster it evaporates. the faster it evaporates, the smaller it becomes. For most of its existence, the process is incredibly slow. A black hole with the mass of our Sun would survive for roughly 10 to the 67th power years. That's a 1 followed by 67 zeros. To appreciate how ridiculous that number is, consider that the universe itself is currently only about 13.8 billion years old. Written as a number, that's roughly 10 to the 10th years. The lifetime of a solar mass black hole exceeds the current age of the universe by an amount so large that our brains struggle to visualize it. And that's not even the biggest example. The largest known black holes contain billions of times the mass of the Sun. Their lifetimes stretch far beyond even those already absurd figures. If the history of humanity were represented by a single second, the lifespan of a giant black hole would still extend beyond the scales that are difficult to meaningfully compare. It's less like comparing a day to a year, and more like comparing a raindrop to an ocean. Yet despite those staggering numbers, the conclusion remains unchanged. Eventually the black hole disappears. Not tomorrow, not next year, not while stars still shine, not while galaxies still resemble galaxies, not even while most familiar structures in the universe continue to exist, but eventually. The process is already underway, right now, at this very moment. Every black hole in the universe is participating in an extraordinarily slow countdown. Some are still growing because they absorb surrounding matter faster than they lose energy. Others are relatively quiet, but the underlying mechanism never completely stops. The leak continues, the clock keeps ticking, and that realization transforms black holes from eternal monuments into temporary residents of the cosmos. Temporary on scales so vast that the distinction hardly seems to matter, yet temporary all the same. There's something wonderfully surprising about that. Black holes often feel like the ultimate winners in the cosmic story. Stars die and become them. Matter falls into them. Light disappears inside them. Gravity gives them extraordinary power. They seem unstoppable, and yet even they are subject to change. Even they have a future. Even they have an ending. The universe appears remarkably unwilling to grant immortality to anything. Stars fade, galaxies evolve, atoms themselves may eventually decay. And black holes, despite their terrifying reputation, are no exception. Of course, realizing that black holes can die only creates a new set of mysteries. Because if a black hole eventually disappears, another question immediately emerges. What exactly is disappearing? What remains trapped inside? Where does all that swallowed matter go? And perhaps most importantly, how can something that seems designed to keep everything forever eventually fade away itself? Several decades ago, if you had asked a physicist whether a black hole could die, the answer would have been remarkably straightforward. No. Not probably not. Not maybe. Simply no. The reasoning behind that answer wasn't based on ignorance or a lack of imagination. Quite the opposite. It came from some of the most successful physical theories ever developed. According to everything scientists understood about gravity, black holes appeared to be the closest thing the universe had to permanence. And honestly, it's easy to see why. Imagine standing at the edge of a deep valley. If you roll a ball down into it, gravity pulls the ball toward the bottom. To get back out, the ball needs energy. Give it enough energy and it escapes. Give it too little, and it rolls back down. This basic idea works throughout the universe. The Earth has gravity. A rocket needs enough speed to escape it. The Sun has gravity. A spacecraft leaving the solar system needs enough speed to escape that. Every massive object creates what physicists call an escape velocity, the speed required to break free from its gravitational pull. For Earth, that speed is about 11 kilometers per second. For the Sun, it's about 618 kilometers per second. The more massive and compact an object becomes, the higher the escape velocity grows. Now imagine squeezing more and more mass into a smaller and smaller space. The gravity becomes stronger, the escape velocity rises. At some point, the required escape velocity becomes so high that it reaches an extraordinary threshold. the speed of light, and that's where black holes enter the story. Light travels at roughly 300,000 kilometers per second. Nothing in the universe can move faster. According to Einstein's theories, that speed limit is fundamental. So what happens when an object's gravity becomes so intense that escaping would require moving faster than light? The answer is unsettlingly simple. Nothing escapes. Not because objects aren't moving fast enough, because moving fast enough is impossible. The boundary where this occurs is called the event horizon. Once something crosses it, every possible future path leads inward. A spaceship cannot escape. A beam of light cannot escape. A radio signal cannot escape. Even information itself appears unable to escape. This is one of the reasons black holes captured the imagination of scientists and the public alike. Most things in the universe still interact with their surroundings. Stars shine, planets reflect light, gas clouds emit radiation. Even the coldest objects usually give off some detectable signal. Black holes seemed different. They appeared completely one-sided. Things could go in, nothing came out. For many physicists, that looks suspiciously like eternity. After all, think about how most objects lose energy. A hot stove cools because heat escapes into the surrounding air. A battery drains because stored energy flows outward. A star shines because energy generated in its core radiates into space. Every familiar process of aging and decay depends on something leaving. Energy leaves, matter leaves, structure breaks down. Black holes seemed exempt from all of it. They swallowed matter, they swallowed energy, they swallowed light. Yet nothing emerged in return. If an object never loses anything, why would it ever disappear? The logic felt almost unavoidable. In fact, early black hole research often treated black holes as the ultimate endpoints of cosmic evolution. A massive star runs out of fuel, it collapses, a black hole forms. The story ends, simple, elegant, final. For a long time, scientists were perfectly comfortable with that picture. The universe creates black holes. Black holes persist forever. Case closed. But science has a habit of becoming uncomfortable whenever something looks too simple. As researchers began studying black holes more carefully during the 20th century, they discovered something fascinating. Even before anyone suspected black holes could evaporate, physicists were uncovering strange clues that suggested black holes behaved almost like living systems. Not literally alive, of course, but surprisingly organized. One important breakthrough came from a series of discoveries during the 1960s and early 1970s. Researchers noticed that black holes obeyed rules that looked strangely familiar. In fact, they resembled the laws of thermodynamics. Thermodynamics is the branch of physics that deals with heat, energy, and entropy. Entropy, loosely speaking, measures disorder or the number of possible arrangements within a system. You can think of it this way. A neatly organized room can become messy in countless ways. A messy room has vastly more possible arrangements than a perfectly tidy one. That's why entropy tends to increase. Nature usually moves towards states with more possibilities. Now here's where things became interesting. Physicists discovered that black holes seemed to possess a quantity that behaved a lot like entropy. The larger the event horizon became, the greater this quantity appeared to be. And remarkably, the area of a black hole's event horizon never decreased. At least according to classical physics. It could stay the same, it could grow, but it could never shrink. This result became known as Hawking's area theorem, although at the time Stephen Hawking himself still believed black holes were eternal. The theorem suggested something profound. Black holes appeared to have an irreversible direction. Just as entropy increases, event horizons could only expand. Throw matter into a black hole, and the horizon grows. Merge two black holes, and the resulting horizon becomes even larger. Everything pointed toward accumulation rather than loss. The universe seemed to be building black holes, not dismantling them. Imagine a bank account that only accepts deposits. No withdrawals, no fees, no spending. Every transaction makes the balance larger. Eventually, you would expect the account to grow forever. Black holes looked a bit like that. Matter falls in, mass increases. Gravity strengthens. The horizon expands. Nothing ever comes back out. Forever appears to be the natural outcome. This idea became even more compelling when scientists studied black hole mergers. Sometimes two black holes orbit each other for millions or billions of years. Gradually they spiral inward. Eventually they collide. The result is one larger black hole. Once again, nothing is lost. The final black hole contains almost all the mass and energy of the originals. It's like two rivers joining into one larger river. The process always seems to move toward bigger structures rather than smaller ones. Even today, observatories regularly detect these mergers through gravitational waves. Every time we observe one, we witness black holes growing. Not shrinking, growing. That reinforces the intuitive picture. Black holes appear to be cosmic collectors. They gather matter, they gather energy, they gather stars. Given enough time, they can consume astonishing amounts of material. At the centers of galaxies, enormous black holes sit surrounded by swirling disks of gas and dust. Some contain millions of solar masses, others contain billions. A few are so large that trying to describe them in ordinary language becomes difficult. Imagine replacing our Sun with a black hole containing 4 million solar masses. That's roughly the size of the supermassive black hole at the center of the Milky Way. The solar system would become almost unrecognizable. Now imagine billions of solar masses. These monsters exist. They sit at the hearts of giant galaxies, patiently feeding over cosmic timescales. Everything about them seems to suggest endurance, persistence, longevity, not death. The more scientists learned, the stronger that impression became. Another reason black holes seemed eternal involved the strange nature of time itself. If you've listened to stories about black holes before, you've probably heard something peculiar. To a distant observer, an object falling toward a black hole appears to slow down. As it approaches the event horizon, its clock seems to tick more slowly. Its movements become increasingly sluggish. The light it emits becomes stretched and reddened. Eventually, the object appears to freeze near the horizon. Now, this doesn't mean the object actually stops. From its own perspective, it continues falling. But from far away, the process appears dramatically slowed. This effect comes from Einstein's theory of general relativity. Strong gravity alters the flow of time. Near a black hole, those distortions become extreme. The closer you get to the event horizon, the more severe they become. For early researchers, this created an additional sense of permanence. Black holes weren't merely objects that trapped matter. They were objects that seemed to push events toward an eternal standstill. Everything about them felt final, timeless, permanent. The universe appeared to have constructed the ultimate storage vault. Nothing escaped, nothing decreased, nothing decayed. And if that wasn't enough, there was another puzzle. Black holes are surprisingly simple. You might expect an object formed from collapsing stars, swallowed planets, and accumulated gas to possess countless complicated features. Yet black holes don't seem to care about most details. Physicists sometimes summarize this with the phrase, "Black holes have no hair." It's an odd expression, but the idea is straightforward. No matter what falls into a black hole, the final object can be described using only a few basic properties. Mass, charge, spin. That's essentially it. Throw in a diamond, throw in a spaceship, throw in a mountain, throw in an entire library containing every book ever written. Once everything crosses the event horizon, the black hole doesn't preserve those visible distinctions. From the outside, only a handful of characteristics remain. That simplicity made black holes seem even more eternal. Complex things often decay because they contain intricate structures that can break down. A castle collapses, a machine wears out, a living organism ages. Black holes appeared almost indestructibly simple. There were very few moving parts. very few opportunities for failure. Nature had seemingly stripped away everything unnecessary. The result looked like the universe's most durable object. By the early 1970s, many physicists viewed black holes as the final state of matter, not necessarily the end of the universe itself, but certainly the end of whatever happened to fall into them. A black hole represented completion, the last stop, the ultimate destination of collapse. Then Stephen Hawking began investigating a question that seemed unrelated. He wasn't initially trying to prove that black holes die. In fact, he expected the opposite. Like most researchers of the era, he assumed black holes were fundamentally eternal. His goal involved understanding how quantum mechanics behaved near an event horizon. At first, it sounded like a technical problem, a mathematical curiosity. One more challenge in the effort to unite gravity and quantum physics. Yet that investigation would eventually overturn one of the most deeply held assumptions in astrophysics. Because when quantum theory entered the picture, something remarkable happened. The perfectly sealed vault suddenly developed a tiny leak. The eternal collector was no longer completely closed. The object that seemed incapable of losing anything turned out to be quietly giving something back to the universe. Not much, not quickly, but enough. Enough to change its fate forever. Enough to transform black holes from immortal cosmic monuments into objects with lifespans. Enormously long lifespans, almost absurdly long lifespans, yet finite ones. And once physicists realized that black holes could lose energy, an entirely new picture of the future began to emerge. A future in which even the darkest and most powerful objects in existence are not exempt from change. A future in which every black hole, no matter how massive, is already participating in a process that will eventually erase it from the cosmos. A curious thing happens whenever people talk about black holes. The conversation almost always focuses on what goes in. Stars fall in, gas falls in, planets fall in, light falls in. Sometimes entire solar systems can eventually find themselves wandering too close and becoming trapped by a black hole's immense gravity. What rarely gets discussed is a much stranger question. What exactly is trapped once it gets there? It sounds simple at first. A black hole swallows something. That thing remains inside. End of story. Yet the moment physicists started examining the idea more closely, the simplicity began to disappear. Because black holes force us to confront one of the most uncomfortable questions in all of science. What does inside actually mean? Tonight, let's move a little closer to the edge of a black hole and explore one of the strangest regions the universe has ever produced. Not because we're planning to jump in, of course. For one thing, the travel arrangements would be extremely inconvenient, but also because understanding what a black hole contains turns out to be essential for understanding how one eventually dies. To begin, let's imagine a massive star nearing the end of its life. Throughout most of its existence, the star has maintained a delicate balance. Gravity pulls inward, nuclear fusion pushes outward. For millions or even billions of years, those forces oppose each other. The star survives because neither side wins. Eventually, however, the fuel begins to run out. Fusion weakens. Gravity gains the advantage. The core collapses. For some stars, the collapse stops when a white dwarf forms. For others, it stops at the neutron star stage. But if the star is massive enough, nothing known can halt the collapse. Gravity keeps squeezing. Matter keeps compressing. The density rises higher and higher, and eventually a black hole forms. At that moment, something extraordinary appears, the event horizon. Earlier, we described the event horizon as a boundary beyond which escape becomes impossible. That's true, but it can also be helpful to think of it another way. The event horizon is not a physical surface. You wouldn't crash into it like a wall. You wouldn't feel a bump. You wouldn't hear a sound. In fact, if you crossed the event horizon of a sufficiently large black hole, you might not immediately notice anything unusual at all. That seems impossible at first. After all, The event horizon is one of the most famous boundaries in the universe. Surely crossing it should feel dramatic, yet physics suggests otherwise. The event horizon isn't made of matter, it isn't a shell, it isn't a membrane. It's a region of space where the geometry of the universe becomes so distorted that every possible route leads deeper inward. Imagine standing on a river. Far upstream, the water moves gently. You can swim against the current. You can move wherever you wish. As you drift closer to a waterfall, the current strengthens. Swimming becomes harder. Eventually you reach a point where the water is moving faster than any swimmer can travel. Beyond that point, escape becomes impossible. No matter how strong you are, no matter how determined, every path leads toward the waterfall. The event horizon works in a somewhat similar way, except instead of water flowing through space, space itself is behaving strangely. Beyond the horizon, every future direction points inward. You're not trapped because something grabs you. You're trapped because the structure of space-time leaves no alternative. And that's where the mystery begins, because once something crosses that boundary, what happens next? Many popular illustrations show objects falling toward a central point. Eventually they reach something called the singularity. The singularity is often described as the center of a black hole, a place where density becomes infinite, a location where the known laws of physics break down. Unfortunately, the word singularity sometimes creates misleading mental images. People imagine a tiny black sphere sitting in the middle of a larger black sphere, almost like a marble inside a hollow shell. Reality appears to be much stranger. According to Einstein's equations, the singularity isn't merely a dense object. It's a region where our mathematical descriptions stop making sense. The quantities we use to describe reality become infinite. Density becomes infinite. Curvature becomes infinite. The equations themselves begin producing answers that physicists generally regard as signs that something important is missing from the theory. When mathematics starts generating infinities everywhere, it's often nature's way of saying, you don't have the full picture yet. And that's exactly the situation we face inside black holes. General relativity predicts singularities. Quantum mechanics dislike singularities. The two theories refuse to cooperate. As a result, nobody currently knows what truly exists at the center of a black hole. That may sound surprising. After all, we've been discussing black holes for decades. We've photographed one. We've detected gravitational waves from black hole collisions. We've observed stars orbiting invisible black holes at galactic centers. Yet the deepest interior remains hidden. Not hidden because scientists are lazy. Hidden because the laws of physics themselves prevent information from reaching us. Anything that happens beyond the event horizon stays beyond the event horizon, at least according to classical physics. It's as though the universe has placed a curtain across the stage. We can infer what might be happening behind it. We can build mathematical models. We can test theories. But direct observation is impossible. This naturally raises another question. If we don't know exactly what's inside a black hole, how can we talk about things being trapped there? The answer is that we know something crossed the horizon. We simply don't know what form it ultimately takes afterward. Suppose an astronaut falls into a black hole. From the astronaut's perspective, they continue inward. They carry their memories. Their body remains intact for a while. Their watch keeps ticking. Their experience proceeds normally, at least initially, but conditions become increasingly extreme. Gravity grows stronger. Space-time becomes more distorted. Eventually, the differences in gravitational force between various parts of the body become enormous. The person's feet may experience significantly stronger gravity than their head. This effect is known as tidal gravity. And in many black holes, it leads to one of the most famously named processes in astrophysics, spaghettification. Yes, that is the actual term. Scientists occasionally display a delightful sense of humour. Spaghettification occurs when tidal forces stretch an object into an increasingly long, thin shape. The part closer to the black hole is pulled harder than the part farther away. The stretching intensifies. Eventually, atoms themselves can be torn apart. Matter becomes elongated into streams. Not a particularly relaxing travel experience. Yet interestingly, this depends heavily on the size of the black hole. Smaller black holes produce stronger tidal forces near the horizon. Larger black holes are surprisingly gentler at first. A supermassive black hole might allow an astronaut to cross the event horizon without immediately noticing anything unusual. The fatal effects would arrive later, deeper inside. Regardless of the details, the important point remains the same. The astronaut cannot escape. Information about their fate cannot return. Something has entered the black hole. Something is trapped. But what exactly survives of the original object becomes increasingly difficult to define, and this is where black holes begin challenging one of our deepest intuitions about reality. In everyday life, objects retain their identities. A book remains a book. A planet remains a planet. A person remains a person. Changes occur, certainly, but information about the object's history generally remains accessible. Black holes seem to erase that distinction. Remember the phrase from the previous section. Black holes have no hair. An odd expression, but an important one. Once matter crosses the horizon, the black hole appears to forget most details. The object that fell in no longer matters. Only a few quantities remain visible from outside. Mass, charge, spin, that's all. Imagine throwing a gold coin into a black hole, then a piano, then a bowl of soup, then every encyclopedia ever written. The black hole grows slightly heavier, but from the outside there is no obvious record of what specifically entered. The details appear lost, and for a long time physicists accepted that conclusion. The information simply disappeared behind the horizon. Problem solved. Or so it seemed. Yet this idea created a growing sense of unease, because information occupies a very special place in physics. Many physical laws suggest that information should never truly be destroyed. Transformed, yes. Scattered, certainly. Hidden, perhaps. But destroyed? That seemed dangerous. Imagine burning a book. The pages vanish. The words disappear. At first glance, the information seems lost, yet in principle, every atom of smoke, every photon of light, every bit of heat still contains traces of what happened. Reconstructing the book would be hopelessly difficult, but the information isn't fundamentally gone, it's merely dispersed. Black holes threatened that principle. They seemed capable of genuine erasure. Throw information in, seal the horizon, never retrieve it. For decades, this remained one of the most troubling implications of black hole physics. What exactly was trapped? Matter, energy, information, all three? And if the information remained trapped forever, perhaps the problem could be ignored. The black hole would simply act as an eternal storage vault, hidden, inaccessible, but permanent. Then Hawking radiation entered the story. Suddenly, black holes were no longer eternal. Suddenly, they could disappear. And that changed everything. Because now physicists faced an alarming possibility. Imagine a black hole forms. It swallows stars. It swallows planets. It accumulates vast amounts of information. Then, after an unimaginable span of time, it evaporates completely. What happens to everything that fell inside? Where does the information go? Does it vanish? Does it escape somehow? Is it stored on the event horizon? Does it emerge encoded within Hawking radiation? Or does something even stranger occur? These questions eventually became known as the black hole information paradox, and despite decades of research, the complete answer remains one of the greatest unsolved problems in theoretical physics. What's fascinating is that the paradox only exists because black holes die. If black holes truly lived forever, information could remain trapped forever. Hidden, perhaps, but still present. The moment black holes gained finite lifespans, physicists were forced to confront a much deeper mystery. The contents of a black hole no longer seemed safely locked away. Eventually, the vault itself would disappear, and when that happened, something had to account for everything that had ever crossed the horizon. Some ideas arrive in science with a dramatic announcement. A telescope spots something unexpected. A laboratory experiment produces a surprising result. A spacecraft sends back an image that changes how we see the universe. The discovery that black holes can die did not happen that way. Instead, it began with a mathematical problem. A very strange mathematical problem. And like many of the most important discoveries in physics, nobody was actually looking for the answer they ended up finding. By the early 1970s, black holes had already become respectable scientific objects. They were no longer considered merely theoretical curiosities. Astronomers had begun finding evidence that these strange gravitational monsters really existed. Physicists were studying their properties in increasing detail. The idea of an event horizon had become part of mainstream science, yet there was a major issue lurking beneath the surface. Two of the greatest theories in physics refused to cooperate. On one side stood general relativity, Einstein's masterpiece, the theory that describes gravity, space, time, planets, stars, galaxies, and black holes. On the other side stood quantum mechanics, the equally successful framework describing atoms, particles, radiation, and the microscopic world. Individually, both theories worked extraordinarily well. Together they behaved like two brilliant musicians trying to play entirely different songs at the same time. Black holes sat directly at the intersection of these competing ideas. Gravity becomes incredibly strong near a black hole. At the same time, quantum effects never completely disappear. Physicists knew that eventually they would need both theories working together. The challenge was figuring out how. One of the researchers exploring this puzzle was Stephen Hawking. At the time, Hawking wasn't attempting to prove that black holes evaporate. Quite the opposite. Like nearly everyone else, he believed black holes should be permanent. The event horizon seemed absolute. Nothing escaped. End of discussion. Yet while investigating how quantum fields behave near black holes, he encountered something deeply unexpected. To understand why the result was so shocking, we first need to talk about empty space. And as strange as it sounds, empty space isn't empty. That statement feels wrong. After all, if a region contains no stars, no planets, no gas, no dust, and no particles, what else could possibly be there? The answer, according to quantum mechanics, is quite a lot. What we call a vacuum is not truly nothing. Instead, it resembles a restless sea of activity. Tiny fluctuations constantly occur. Energy appears, energy disappears. Particle pairs emerge, particle pairs vanish. All of this happens incredibly quickly. Normally, these microscopic events are so brief that they leave no lasting trace. You might imagine them as tiny ripples forming and disappearing on the surface of an enormous ocean. Most of the time, the ocean looks calm. Yet beneath that calm appearance, countless small disturbances are constantly occurring. Quantum physics predicts something similar throughout the universe. Even the emptiest regions of space are busy. Not busy in a way we can directly observe with our eyes. Busy in a deeper, more fundamental sense. Virtual particles appear, virtual particles disappear. The vacuum never truly rests. Now, if you're lying comfortably in bed listening to this, you may be wondering how tiny quantum fluctuations have anything to do with giant black holes. That's exactly what made Hawking's discovery so remarkable. The connection wasn't obvious. Imagine two particles appearing together near the event horizon. Under normal circumstances, they would quickly annihilate one another. The fluctuation would end. The vacuum would return to its previous state. Nothing interesting would happen. Near a black hole, however, the situation becomes more complicated. The event horizon introduces an extreme gravitational environment. And extreme environments often force physics to reveal behaviors that remain hidden elsewhere. Suppose one member of a particle pair appears just outside the horizon. Suppose the other appears slightly closer to the black hole. Normally they would reunite, but the gravity near the horizon can separate them before that happens. One particle falls inward, the other escapes. Suddenly the pair can no longer cancel itself out. The process leaves behind a real particle moving away from the black hole. To a distant observer, it looks as though the black hole has emitted something. That alone was startling. After all, black holes are not supposed to emit anything. They're famous for doing exactly the opposite. Everything falls in, nothing comes out. Yet quantum mechanics seem to be whispering a different story. Not a loud story, not a dramatic one, a tiny story, a faint story, but a story nonetheless. The black hole appeared to be glowing, very faintly. Today we call that glow Hawking radiation. The name sounds almost ordinary now because generations of students have encountered it in textbooks. At the time, however, the idea was revolutionary. Many physicists initially found it difficult to accept. After decades of treating black holes as eternal prisons, they suddenly faced a radically different picture. Black holes were leaking. Not much, not quickly, but enough. And once energy starts leaving a system, consequences follow. Consider a campfire. The fire emits light and heat. That energy comes from somewhere. It comes from the wood. As energy leaves, fuel decreases. Eventually the fire burns out. The same principle applies throughout physics. Whenever energy escapes, something changes. A black hole emitting Hawking radiation must pay a price. The price is mass. Einstein's famous equation tells us that mass and energy are related. Energy leaving means mass leaving. Mass leaving means the black hole shrinks. And there, hidden inside a subtle quantum effect, lay one of the most astonishing conclusions in modern science. Black holes can evaporate. The word evaporate sometimes creates amusing mental images. People picture steam rising from a kettle, or water disappearing from a puddle after rain. Black hole evaporation is much slower, far slower. A puddle may evaporate over days, a lake may take years. A black hole takes timescales so immense that ordinary language struggles to describe them. Let's look at an example. A black hole with the mass of our Sun would survive for roughly 10 to the 67th power years. That number is almost impossible to visualize. The current age of the universe is about 13.8 billion years. Compared with a black hole's lifespan, the universe itself is still astonishingly young. It's as though we've arrived at the beginning of a movie after watching only the studio logo. The actual story has barely started. Yet even more surprising is what happens as evaporation continues. Most things cool down as they lose energy. A cup of tea cools, a campfire cools, a heated stone cools. Black holes behave differently. As a black hole loses mass, its temperature rises. Smaller black holes become hotter. Hotter black holes emit more radiation. More radiation means faster mass loss. Faster mass loss means even higher temperatures. It's a runaway process, a feedback loop. The black hole spends most of its existence changing very slowly. Then, near the end, everything accelerates dramatically. Imagine a giant hourglass. For billions upon billions of years, almost no sand appears to move. Then suddenly the final grains rush downward. The ending arrives much faster than the beginning. That's roughly how black hole evaporation behaves. The largest black holes remain stable-looking for unimaginable stretches of time. Only near the very end does the process become dramatic. At first, Hawking himself was surprised by the implications. The calculation seemed correct. The mathematics worked. Yet the conclusion contradicted decades of assumptions. The universe had apparently hidden a tiny escape hatch inside the most inescapable objects ever discovered. This realization transformed our picture of cosmic history. Before Hawking radiation, black holes represented endpoints, permanent destinations, final states. After Hawking radiation, they became temporary. Extremely long-lived temporary objects, but temporary all the same. That distinction matters. Imagine reading a story in which a castle stands forever. No matter what happens around it, the castle remains. Then imagine discovering that the castle is slowly disappearing grain by grain. The process is almost imperceptible, yet it changes the entire narrative. The ending becomes different. The future becomes different. The meaning of permanence changes. Black holes underwent a similar transformation. For the first time, physicists could imagine a universe in which every black hole eventually vanishes. No exceptions. Not the small ones. Not the supermassive ones. Not the giants lurking at galactic centres. Every single one. Given enough time. And enough time remains one of the most important phrases in this discussion, because Hawking radiation is extraordinarily weak. If you could somehow observe a supermassive black hole up close, it would not resemble a glowing furnace. It would be colder than the cosmic microwave background. In fact, most large black holes currently absorb far more energy from their surroundings than they lose through Hawking radiation. They are still gaining mass overall. The leak exists, but the leak is tiny. Picture a giant reservoir containing trillions upon trillions of litres of water. Now imagine a single droplet escaping every so often. Technically, the reservoir is losing water. Practically, the change is almost impossible to notice. That's roughly where today's black holes find themselves. The evaporation process has begun. Yet for many of them, the universe simply isn't old enough for us to witness meaningful effects. The really dramatic stages belong to a future beyond anything familiar, a future beyond stars, beyond galaxies as we know them, beyond nearly everything currently visible in the night sky. And that realization introduces another fascinating perspective. At this moment, black holes are among the youngest things in the universe. Not individually, of course. Some formed billions of years ago. But relative to their total lifespans, they're still near the beginning. A human reaching age 20, in an 80-year lifespan, has already lived a quarter of their life. A black hole existing for billions of years may have completed only an unimaginably tiny fraction of its journey. The vast majority of its existence still lies ahead. Somewhere in that distant future, evaporation will eventually dominate. Accretion will stop. Growth will end. The slow leak will become impossible to ignore, and black holes will begin the long transition from cosmic collectors to cosmic remnants. Yet Hawking radiation created another problem, a very serious one, perhaps the biggest mystery in black hole physics. Because if black holes evaporate, what happens to everything they swallowed? The radiation emerging from a black hole appears random, thermal, featureless. But stars, planets, books, people and galaxies contain information. Huge amounts of information. If the black hole eventually disappears completely, where does all that information go? Does it escape somehow? Was it secretly stored on the horizon all along? Does quantum mechanics preserve it? Or is something even stranger happening? The leak Hawking discovered did more than give black holes an ending. It opened one of the deepest puzzles in modern science, a puzzle that remains unresolved even today. Picture an hourglass so enormous that entire civilizations could rise, flourish, vanish, and be forgotten before a single grain of sand visibly moved. That's probably the closest everyday comparison we have to black hole evaporation. One of the challenges in discussing black holes is that our brains are built for human timescales. We understand seconds. We understand years. We can even wrap our minds around centuries if we try hard enough. But black holes operate on schedules that make those units feel almost irrelevant. When physicists say a black hole evaporates slowly, they're using the word slowly in perhaps the most extreme way it has ever been used. Let's begin with a simple thought experiment. Imagine creating a black hole with exactly the same mass as our Sun. Not a supermassive monster, not one of the giants lurking in galactic centres, just a black hole containing one solar mass. How long would it survive? The answer is roughly 10 to the 67th power years. A 1 followed by 67 zeros. Numbers like that quickly stop feeling meaningful, so let's build some perspective. The universe today is approximately 13.8 billion years old. Written scientifically, that's about 10 to the 10th years. A solar mass black hole lives for about 10 to the 67th power years. That means its lifespan exceeds the current age of the universe by a factor of roughly 10 to the 57th power. Even saying that aloud doesn't really help. It's like trying to compare a single grain of sand to an entire planet. The difference is so vast that normal intuition breaks down. And remember, we're not discussing one of the largest black holes. We're discussing a relatively ordinary one. The truly massive black holes survive for far longer. A supermassive black hole containing billions of solar masses can remain intact for around 10 to the 100th years, or even longer. That's a number so large that it has earned its own nickname, a googol. Not Google, the company. Google. One followed by 100 zeros. It's one of those rare moments when mathematics starts sounding like science fiction. Yet these estimates come directly from accepted physical theories. If Hawking radiation behaves the way we currently believe it does, black holes genuinely survive for these staggering lengths of time. Naturally, this raises an important question. What exactly are they doing during all those years? The answer is both simple and surprising. For most of their lives, almost nothing noticeable happens. The evaporation process is astonishingly weak. Imagine taking a gigantic iceberg and removing a single water molecule every few hours. Technically, the iceberg is shrinking. Practically, it looks unchanged. Year after year, century after century, millennium after millennium. The same basic idea applies to black holes. They lose mass continuously, but the amount lost is incredibly small. In fact, large black holes emit less Hawking radiation than small ones. That's because black hole temperature behaves in a counterintuitive way. Most objects become cooler as they get larger. A giant ocean changes temperature more slowly than a small puddle. A massive building retains heat differently than a small shed. Black holes take this trend to an extreme. The larger the black hole, the colder it becomes. A stellar mass black hole is already extraordinarily cold. A supermassive black hole is colder still, much colder, far colder than interstellar space, far colder than anything humans could naturally experience. This means large black holes radiate energy at an incredibly slow rate. Their evaporation resembles a tiny leak from an enormous reservoir. For billions upon billions of years, the leak barely matters, and that's fortunate for the black holes, because today's universe contains plenty of material they can still consume. Gas clouds drift through galaxies, stars orbit galactic centers, dust and radiation fill space. Many black holes continue gaining mass faster than they lose it. Imagine a bathtub with a small drain open. If the faucet pours water in faster than the drain removes it, the water level rises. The leak exists, but growth dominates. That describes many black holes today. The evaporation process is real, yet their surroundings still provide additional fuel. This situation won't last forever. The universe itself is changing. Stars are gradually exhausting their nuclear fuel. Galaxies are evolving. The supply of easily available matter is shrinking. Eventually, the era of active black hole growth begins to fade. To understand why, we need to think on truly cosmic timescales. Right now, we live during what astronomers sometimes call the stelliferous era, the age of stars. The universe is filled with starlight. Fusion powers galaxies. New stars continue forming. The night sky remains active and luminous. This era lasts for trillions of years, a very long time by human standards. Yet from the perspective of black holes, it is merely the opening act. As trillions of years pass, star formation gradually slows. Gas reserves become depleted. Fewer new stars appear. Existing stars continue aging. White dwarfs accumulate. Neutron stars accumulate. Black holes accumulate. The universe slowly grows darker. Not suddenly, not dramatically. Gradually, the way evening settles across a landscape. One source of light disappears, then another, then another. Eventually, most stars have completed their lives. Some leave white dwarfs behind, others leave neutron stars, the most massive leave black holes. By this point, black holes begin dominating the universe's inventory of compact objects. They become some of the most important structures remaining, and still they survive, still they endure. Still Hawking radiation remains incredibly weak. Many trillions of years pass, then many trillions more. Galaxies themselves begin changing beyond recognition. Close encounters between stars and remnants gradually eject objects into intergalactic space. Orbits become unstable. Structures slowly unravel. What once looked like familiar galaxies become increasingly sparse. The universe continues expanding. Distances grow. Isolation increases. Yet black holes remain. Patient. Silent. Ancient. If you could somehow witness this future, black holes would seem almost eternal. Everything else would be changing around them. Everything else would be fading. Meanwhile, the black holes would appear stubbornly unchanged. That appearance, however, would be deceptive. The leak never stops, every second. Every minute, every year, every trillion years, energy continues escaping. Mass continues decreasing. The process remains tiny, but it remains relentless. Nature is remarkably persistent. A process doesn't need to be fast if it has enough time. Consider water dripping onto stone. One drop accomplishes almost nothing. 1,000 drops accomplish little more, but given centuries, even stone begins to yield. Hawking radiation operates according to the same principle. The leak is weak. The timescale is enormous. The cumulative effect becomes unavoidable. Eventually, black holes stop gaining more mass than they lose. For the first time, evaporation truly takes control. And that's when the long decline begins. One of the strangest aspects of this decline is that it accelerates as it progresses. Most forms of decay slow down over time. A fire becomes weaker as fuel disappears. A spinning top gradually loses momentum. A battery's output declines. Black holes behave differently. Remember what we discussed previously. As a black hole loses mass, its temperature increases. Higher temperature produces more Hawking radiation. More Hawking radiation removes mass faster. The black hole becomes hotter still. It's a positive feedback loop. The process feeds itself. At first, the acceleration is almost impossible to notice. The black hole remains enormous. The temperature increase remains tiny. But over sufficiently long periods, the effect becomes significant. Imagine rolling a snowball downhill in reverse. Instead of collecting more snow, it slowly sheds material. At first, the change is subtle. Then the snowball becomes smaller, then smaller still. Eventually, loss begins accelerating. The final stages arrive far more quickly than the opening ones. For black holes, the vast majority of their lifespan occurs during the early slow phase. They spend almost all of existence as giant, stable-looking objects. The dramatic ending occupies only a tiny fraction of the total timeline. This is one reason black hole evaporation remained difficult to imagine even after Hawking's discovery. Human intuition naturally focuses on dramatic events, explosions, collisions, sudden transformations. Black hole death is mostly the opposite. It's patience elevated to a cosmic principle, a process unfolding across intervals so immense that entire eras of the universe pass while the black hole barely notices. In fact, if a black hole could somehow think, it might regard the age of stars as a brief youthful memory. The rise and fall of galaxies would seem like temporary weather. Civilizations would appear and vanish too quickly to observe. Even the current age of the universe would occupy only the tiniest sliver of its lifespan. Yet despite all that longevity, the outcome remains fixed. The black hole shrinks, the temperature rises, the radiation intensifies, the leak grows, the future approaches. And as the black hole becomes smaller, the character of the process begins changing. A giant black hole radiates so weakly that detecting Hawking radiation directly is almost impossible. A much smaller black hole would behave very differently. It would become hotter, brighter, more active. The evaporation process would no longer resemble a barely detectable leak. Instead, it would start looking increasingly energetic. The black hole would transform from a nearly invisible absorber into an object actively shedding energy. That transition remains unimaginably far away for the black holes we observe today. None are anywhere close to reaching it, not even remotely close. Yet according to current theory, the transition is inevitable. The clock may tick slowly, absurdly slowly, but it still ticks. Far beyond the age of stars, beyond the age of familiar galaxies, beyond the age in which any human-built clock could still have meaning, the universe becomes a very different place. Not because something dramatic suddenly happens, not because a cosmic catastrophe sweeps across existence. The transformation arrives gradually, almost quietly. The night sky that we know today is filled with activity. Stars burn, nebulae glow, galaxies collide, new worlds form around young suns, radiation pours across space in every direction. The future is not like that. The future grows older, and as the universe ages, it also grows emptier. If you are somehow able to travel forward trillions upon trillions of years, one of the first things you would notice is the absence of light. Not complete darkness, not yet. But the brilliant universe we know today would already be fading. Most stars would have exhausted their fuel long ago. The brightest stellar populations would be gone. The enormous nurseries where new stars once formed would have largely disappeared. The universe would still contain matter, but much of it would exist in colder, quieter forms. White dwarfs, neutron stars, brown dwarfs, and black holes. Lots of black holes. Tonight we're going to explore a surprisingly important moment in this distant future. The last meal a black hole will ever eat. Because before black holes become isolated relics slowly evaporating into nothingness, they must first reach a point where the universe can no longer feed them. That turning point marks the beginning of the end, and oddly enough, understanding that moment requires us to think less about black holes themselves and more about the future of everything around them. Right now, black holes live in a relatively rich universe. Matter is everywhere. Gas drifts through galaxies. Stars orbit galactic centers. Dust clouds stretch across interstellar space. Entire planets wander through cosmic darkness. The universe contains an enormous buffet of material waiting to be consumed. Not every black hole is actively feeding, of course. Many are relatively quiet. But the opportunity exists. If matter strays too close, gravity takes over. The black hole grows. This growth process has shaped much of cosmic history. The supermassive black hole at the center of our Milky Way currently contains about 4 million times the mass of the Sun. That mass did not appear all at once. It accumulated gradually, generation after generation, star after star, cloud after cloud. For billions of years, the black hole collected material from its surroundings. Many other galaxies contain even larger examples. Some central black holes contain billions of solar masses. Their growth histories stretch across much of cosmic time. In a sense, black holes are professional eaters. They spend their lives gathering, absorbing, accumulating, growing. And yet even the most successful feast eventually ends. The reason is simple. The universe is not creating unlimited new food. The supply is finite. Let's begin with stars. Stars are the great engines of the cosmos. They convert hydrogen into heavier elements. They produce light. They generate heat. They create the raw materials from which planets and living things eventually emerge. For a while, the universe was extremely good at making stars. Billions upon billions of them. Entire galaxies glittered with fresh stellar populations. The peak of star formation occurred billions of years ago. Back then, galaxies contained abundant cold gas, Raw fuel was everywhere. New stars formed rapidly. The universe was busy, young, energetic. That era does not last forever. Every star that forms consumes part of the available fuel supply. Hydrogen becomes helium. Helium becomes heavier elements. Gas reservoirs gradually shrink. As billions of years pass, star formation slows. Astronomers already observe this trend today. The universe is producing fewer stars than it once did. The cosmic baby boom is over. The population is aging. Given enough time, this process continues. Trillions of years into the future, star formation becomes increasingly rare. The raw materials still exist in some places, but the universe no longer resembles the active stellar factory we see today. Imagine a city where factories gradually close one by one. Production slows. New construction becomes uncommon. Existing buildings remain, but the pace of growth declines. Something similar happens on a cosmic scale. The universe keeps operating, it simply becomes less productive. This matters enormously for black holes. Every star that fails to form is one less future meal. Every depleted gas cloud is one less source of mass. Every exhausted reservoir reduces future opportunities for growth. Yet stars are only part of the story. Galaxies themselves also evolve. Today, galaxies appear relatively stable. The Milky Way contains hundreds of billions of stars orbiting a common centre. Large-scale structures remain recognizable across billions of years. But on sufficiently long timescales, even galaxies begin changing. Gravity is constantly reshaping stellar orbits. Close encounters occur. Energy gets exchanged. Some stars gain velocity, others lose it. The process is slow, but over trillions of years, those tiny interactions accumulate. Imagine a crowded room. People move around randomly. Eventually some drift toward the exits. Others gather in clusters. Given enough time, the original arrangement disappears. Galaxies behave similarly. Stars are gradually ejected. Orbits are rearranged. Structures become less organized. Astronomers sometimes call this process gravitational relaxation. The name sounds peaceful. The consequences are anything but. Entire galaxies slowly unravel. Stars that once orbited comfortably inside galactic systems may eventually find themselves drifting through intergalactic darkness. Over sufficiently long periods, galaxies lose members. They become increasingly sparse, the universe grows lonelier. This has profound implications for black holes. A black hole can only consume matter that comes near it. If stars are scattered across enormous distances, feeding opportunities become increasingly rare. The giant buffet begins disappearing, not because the food is gone, because it is becoming harder to reach. Meanwhile, many stars themselves are changing. The most massive stars died long ago. Medium-sized stars eventually follow. Even red dwarfs, famous for their extraordinary longevity, ultimately exhaust their fuel. What remains are stellar remnants, white dwarfs, neutron stars, black holes, cold objects occupying an aging universe. At this stage, black holes still possess opportunities for growth. White dwarfs can be captured, neutron stars can be captured, other black holes can be captured. The feast continues, but the menu becomes increasingly limited. The universe is serving leftovers, yet black holes remain patient. Patience is one thing they have in abundance. A black hole does not care whether a meal arrives tomorrow or 10 trillion years from now. Gravity waits, and gravity rarely becomes bored. Suppose a wandering white dwarf passes too close. The black hole consumes it. Suppose two black holes eventually collide. A larger black hole forms. Suppose a neutron star drifts inward. Another meal arrives. These events become less frequent over time, but they still occur. For immense stretches of cosmic history, black holes continue growing. Very slowly, very sporadically, but growing nonetheless. Then comes a remarkable transition. Eventually, the universe reaches a point where growth and evaporation become comparable. This is not a sudden event. No cosmic alarm sounds. No universal announcement is made. Yet it represents one of the most important turning points in black hole history. For billions upon billions of years, black holes mostly gain mass. Then, for a period, gains and losses become roughly balanced. After that, evaporation begins winning. For the first time, the black hole's future points consistently downward. The feast is ending. Imagine a business that has spent centuries expanding. New customers arrive constantly. Revenue grows. Success seems inevitable. Then growth slows. New customers become rare. Income levels off. Eventually more money leaves than enters. The company is still functioning, but its direction has changed. Black holes experience a similar shift. For most of cosmic history, they are accumulators. After this transition, they become spenders. Not voluntarily, of course. Hawking radiation forces the issue. Energy keeps leaking away. Mass keeps disappearing. And without fresh material arriving, nothing replaces the loss. This is what makes the last meal so important. Every black hole eventually consumes something for the final time. The object might be a star, a white dwarf, a neutron star, another black hole. The specifics depend on the black hole's environment. But eventually there comes a final addition to its mass. The last deposit, the last successful feeding event, the last growth spurt. After that, only decline remains. Interestingly, nobody can predict exactly what that final meal would be for any particular black hole. The future becomes too chaotic, too dependent on countless interactions across unimaginable timescales. Yet statistically, the outcome is unavoidable. Sooner or later, the supply runs out. The universe simply becomes too empty. Distances become too large. Encounters become too rare. Growth becomes impossible. What makes this especially fascinating is that the black hole itself may remain enormous. The final meal does not occur near the end of the black hole's life, not even close. A supermassive black hole may stop feeding long before it begins its most dramatic evaporation stages. In human terms, it would be like finishing your last meal while still having millions of years left to live. The feast ends early. The waiting lasts much longer. This creates one of the strangest periods in cosmic history. The universe enters an era where black holes dominate the landscape, yet many are no longer growing. They have reached their maximum size, the largest they will ever be, the heaviest they will ever be, the most powerful they will ever be. From that point onward, every change moves in one direction: smaller, lighter, closer to disappearance. Of course, even then the process remains extraordinarily slow. A giant black hole does not suddenly shrink before anyone's eyes. The evaporation continues at its usual glacial pace. Millions of years pass, then billions, then trillions. The black hole remains, ancient, silent, almost unchanged. Yet the direction is different now. The future no longer contains growth, only erosion. A tiny leak steadily removing mass from one of the most durable objects in existence. There is something oddly poetic. Not poetic in the decorative sense, but in the sense of simple inevitability about that transition. For billions of years, gravity acts as a collector, gathering, accumulating, building. Then the collection phase ends. No more stars arrive, no more gas clouds arrive, no more wandering remnants arrive. The black hole keeps existing, but it has already eaten its final meal. It just doesn't know it yet. From our perspective, that moment lies so far in the future that it almost sounds fictional. Yet according to everything we currently understand, it is a real stage in cosmic evolution. The universe is not infinitely productive. Resources are finite. Opportunities diminish. Growth eventually stops. Even black holes must confront that reality. And once the final meal is passed, a new age begins, an age unlike anything we see today, an age where black holes become the dominant surviving objects in an increasingly dark universe. Nothing in human experience prepares us for the black hole era, not the rise and fall of civilizations, not the lifetimes of stars, not even the age of galaxies. The period we're about to explore is so distant that nearly everything familiar has already disappeared. If the current universe feels ancient to us, the black hole era belongs to a future so remote that today's cosmos would seem almost newborn by comparison. And yet, according to our best understanding of physics, this era may become one of the longest chapters in the entire history of existence. By the time it arrives, the universe has already changed beyond recognition. The bright age of stars is over. The galaxies that once filled space with billions of shining suns have largely gone dark. The great stellar nurseries stopped producing new generations long ago. The familiar constellations vanished ages earlier. Even the Milky Way itself no longer resembles the galaxy we know tonight. Most of the stars that once illuminated the cosmos have completed their lives. The larger stars died first. Medium-sized stars followed. Eventually, even the remarkably long-lived red dwarfs exhausted their fuel. For trillions upon trillions of years, stellar evolution slowly erased the universe's primary source of light. At first, remnants remained. White dwarfs lingered. Neutron stars endured. Brown dwarfs drifted through the darkness. Yet time kept moving forward. And time, given enough of it, changes everything. Let's imagine what an observer might see during this distant future. Assuming such an observer could somehow exist, the sky would appear profoundly different. Today, when we look upward, we see stars in every direction. Future observers would not. Most of the sky would be dark. Not because vision had failed, not because something blocked the light, simply because the light itself would be gone. The universe would have become an increasingly quiet place. That quietness emerges gradually. There is no specific date when someone announces that the age of stars has officially ended. Instead, the cosmic population slowly ages. One source of light disappears, then another, then another. The process unfolds over intervals so vast that the transition feels almost geological in nature. A mountain does not suddenly become a valley. An ocean does not suddenly become a desert. Large transformations often arrive through accumulation. The black hole era emerges in the same way. Eventually, black holes become the dominant surviving structures, not necessarily because they are actively doing anything. In many cases, they aren't. They're simply outlasting everything else. It's a little like being the last building standing after a city slowly empties. The building hasn't changed much. The surroundings have. One reason black holes dominate this future is their extraordinary durability. We've already discussed how slowly Hawking radiation operates. Even after star formation ends and galaxies evolve beyond recognition, black holes remain, and remain, and remain. A stellar mass black hole survives for approximately 10 to the 67th power years. The largest supermassive black holes survive for timescales approaching 10 to the 100th years. Those numbers are difficult to grasp because nothing else in ordinary experience survives for comparable durations. Human civilizations measure their histories in centuries. Species measure their histories in millions of years. Planets survive for billions. Stars may endure for trillions. Black holes push longevity into entirely different territory. As a result, they become the defining objects of this future universe. Now, despite the name black hole era, it would be misleading to imagine a universe packed densely with black holes. Quite the opposite. The universe continues expanding throughout this entire period. Galaxies drift farther apart. Distances grow larger. Space becomes increasingly empty. The surviving black holes are separated by enormous expanses of darkness. Picture an ocean so vast that individual islands are separated by distances almost beyond imagination. Now make the ocean much larger, then larger again. That's closer to the scale we're discussing. The black hole era is not crowded, it is extraordinarily lonely. One fascinating consequence of cosmic expansion is that interactions become increasingly rare. Today's universe remains dynamic. Galaxies collide, stars pass near one another, gas clouds interact, matter remains relatively accessible. Future black holes live under very different conditions. Potential meals become scarce. Close encounters become uncommon. The universe stretches itself thin. For many black holes, millions of trillions of years may pass without any significant interaction whatsoever. They simply exist. Silent, dark, patient. At this point, you might wonder whether anything interesting still happens. After all, if stars are gone and black holes spend most of their time alone, does the universe become completely static? Not entirely. Rare events continue occurring, and because the timescales are so vast, even incredibly unlikely events eventually happen somewhere. For example, some stellar remnants may still encounter black holes. A wandering white dwarf could drift too close. A neutron star might eventually be captured. In especially fortunate circumstances, two black holes could still meet and merge. Such events become much rarer than they are today, but rarity means something different when you're discussing intervals measured in trillions upon trillions of years. Given enough time, unlikely things become inevitable. Think about rolling dice. Rolling a 6-10 times in a row is extraordinarily unlikely. But if you roll long enough, eventually strange sequences appear. The universe operates similarly. Time is nature's greatest opportunity generator. The longer something continues, the more chances there are for unusual outcomes. So mergers still occur, occasional captures still occur. Yet the overall trend remains clear. Growth is ending. Evaporation is beginning to dominate, and that changes the role black holes play within the cosmos. Earlier in their lives, black holes function as collectors. Matter flows inward, mass increases, gravity strengthens, the future points toward growth. The black hole era reverses that story. The surviving giants are no longer primarily gathering material. Instead, they are very slowly giving material back. Not through dramatic outbursts, not through explosions, through Hawking radiation. The same subtle process we discussed earlier continues operating throughout this age. The difference is that evaporation now matters more than feeding. The black holes are spending their accumulated reserves. Imagine a wealthy individual who spent centuries building a fortune. Eventually income stops arriving. No new deposits appear. The fortune begins shrinking. At first, the decrease is barely noticeable. The reserves are enormous, but the direction has changed. The same thing happens to black holes. For billions upon billions upon billions of years, they accumulated mass. Now they begin spending it. The leak remains tiny, yet the leak never stops. One especially strange feature of the black hole era involves temperature. Large black holes remain extraordinarily cold, much colder than almost anything else, but as evaporation progresses, temperatures rise. This creates an unusual future. The oldest black holes gradually become more energetic as they become smaller. Most objects cool as they age. Black holes eventually do the opposite. The process unfolds so slowly that it barely resembles ordinary aging. Yet the trend is real. A shrinking black hole is a warming black hole. A warming black hole emits more radiation. More radiation accelerates mass loss. The feedback loop slowly strengthens. At first, the effect is negligible. Then it becomes noticeable. Eventually, it becomes dramatic, but we are not there yet. The black hole era spends most of its existence in the slow phase. The giants remain giants. The evaporation remains weak. Patience continues to dominate the story. Another remarkable aspect of this future concerns information. Earlier we discussed the information paradox. Everything swallowed by a black hole appears trapped behind the event horizon. Stars, planets, gas, radiation, perhaps entire histories of vanished solar systems. During the black hole era, much of that information remains hidden. The black holes act like enormous archives, silent records of countless cosmic events. A supermassive black hole that survives into this era may contain material accumulated across billions of years of galactic history, ancient stars, destroyed worlds, matter that once participated in processes no longer occurring anywhere in the universe. In a sense, these black holes become cosmic museums. Not museums anyone can visit, not museums anyone can read, but repositories nonetheless. The past remains locked away inside them. For now. That phrase is important. For now. Because Hawking radiation ensures the archives are not permanent. Eventually the black holes themselves disappear. And that raises one of the deepest questions in physics. What happens to everything they contain? The black hole era becomes the stage upon which that mystery unfolds. As evaporation proceeds, the universe slowly approaches a confrontation with one of its greatest unanswered problems. Yet before we reach that point, it is worth pausing to appreciate just how extraordinary this age truly is. Consider everything that must already have happened before the black hole era even begins. Every civilization in Earth's history. Every future civilization that may ever exist. Every mountain currently standing. Every ocean. Every forest. Every species. Every star visible tonight. All gone. Not recently gone. Gone for durations so vast that their existence belongs to an almost incomprehensibly distant past. The dinosaurs feel ancient to us because they lived tens of millions of years ago. The black hole era begins after intervals larger by factors that defy ordinary comparison. If an observer somehow existed during this future, the age of stars would seem almost mythical. Perhaps even more distant than mythology. It would belong to a past so remote that reconstructing it might appear impossible, and still black holes would remain. That endurance explains why they inherit the universe. Not because they conquer it, not because they dominate it through activity, simply because they survive. The cosmos gradually sheds nearly everything else. The black holes stay behind, at least for a while. Yet permanence remains an illusion, even here, even now, even during the longest-lived age of all. The leak continues, the temperatures rise, the masses shrink, long before a black hole reaches its final moments, long before the last burst of radiation, and long before the universe witnesses its ultimate disappearance. There comes a stage that might be even more fascinating. The black hole begins to change in ways that would have seemed impossible during its youth. For most of its existence, a black hole appears almost permanent. Its mass remains enormous. Its event horizon remains vast. Its temperature remains incredibly low. If you observed it over millions, billions, or even trillions of years, you would struggle to notice any difference at all. The giant seems frozen in time, stable, unchanging, eternal. That impression is one of the greatest illusions in the universe, because underneath that calm exterior the leak never stops. Every second, Hawking radiation carries away a tiny amount of energy. Every second, the black hole becomes very slightly lighter. Every second, it moves one microscopic step closer to an ending that lies unimaginably far ahead. For countless ages, those changes are effectively invisible. Imagine trying to watch a mountain erode one atom at a time. The process is real. The mountain is changing. Yet the transformation occurs so slowly that no observer could directly perceive it. Black holes spend most of their lives in a similar state. They are fading. But they are fading with extraordinary patience. Eventually, however, patience begins to run out. Not because the black hole decides to do anything differently. Because physics itself starts changing the pace of the story. To understand why, let's revisit one of the strangest facts about black holes. The smaller they become, the hotter they become. This still sounds backward. Almost everything in everyday experience behaves the opposite way. A large pot of water cools slowly, a small cup cools quickly. A massive object generally stores more energy than a tiny one. Black holes refuse to follow our intuition. A large black hole is cold. An even larger black hole is colder. A smaller black hole is warmer. And as evaporation continues, the temperature keeps rising. At first, the increase is tiny. A supermassive black hole may spend unimaginable stretches of time growing only slightly warmer. The difference is almost meaningless, but remember what kind of timescales we are discussing. The black hole era itself may last for periods approaching a Google years, given intervals that vast, tiny changes eventually become important. Imagine placing one sheet of paper on a table every century. The stack grows very slowly. After 1,000 years it remains unimpressive. After 1,000,000 years it becomes substantial. After enough time, even tiny contributions accumulate into something impossible to ignore. The same principle governs black hole evaporation. The temperature rise begins almost invisibly. Then it slowly becomes significant. As temperature increases, radiation increases. As radiation increases, mass loss accelerates. As mass loss accelerates, temperature rises further. The feedback loop that existed throughout the black hole's life gradually becomes stronger. For much of its existence, the black hole resembles a giant reservoir leaking through a microscopic crack. Eventually the crack widens. Not dramatically, not suddenly, but enough to matter. Suppose we could somehow visit a supermassive black hole during this distant future, not one from our era. One that has already spent incomprehensible ages evaporating. At first glance, it would still appear enormous. Its event horizon would remain vast. Its gravity would remain powerful. Yet compared to its younger self, subtle changes would already be underway. Its mass would be lower. Its temperature would be higher. Its remaining lifespan would be shorter. The giant has begun aging. That's an interesting word to apply to a black hole. Aging. We usually reserve it for living creatures. People age. Animals age. Trees age. Yet black holes possess their own version of a life cycle. They are born through gravitational collapse. They grow through accretion. They mature through long periods of stability. And eventually they begin declining. The difference is that their old age lasts longer than most entire eras of cosmic history. This future decline produces a fascinating visual transformation. A young, supermassive black hole is extraordinarily cold. Its Hawking radiation is almost undetectable. A much older black hole emits more radiation. Still not enough to light up the universe. Still not enough to resemble a star. But enough that the trend becomes unmistakable. The object is becoming increasingly active. The strange thing is that this increased activity signals weakness rather than strength. When a star becomes brighter, we often associate that with power. A bright lighthouse is easier to notice than a dim one. A blazing fire feels more energetic than a dying ember. Black holes reverse that intuition. A warming black hole is a shrinking black hole. A shrinking black hole is a dying black hole. Its increasing activity represents loss. The brighter it becomes, the closer it moves toward disappearance. Imagine watching a candle that burns more intensely as it runs out of wax. The flame grows stronger precisely because the end is approaching. That isn't how ordinary candles behave. It is remarkably similar to how black holes behave. As the ages pass, the universe itself continues changing around these fading giants. By now, the cosmos is extraordinarily dark. Most familiar sources of light vanished long ago. Galaxies no longer resemble galaxies. Stars are rare relics of an ancient past. The black holes dominate not because they are abundant, but because so little else remains. Against this dark backdrop, the increasing radiation becomes more noticeable. Not because it is enormous, because the competition has disappeared. It's easier to notice a whisper in an empty room than during a crowded concert. The universe of the black hole era is becoming increasingly empty. As a result, even modest emissions stand out more clearly. There is another fascinating consequence of the shrinking process. The event horizon itself gradually contracts. The boundary that once enclosed vast amounts of space slowly retreats. The black hole's gravitational reach remains significant, but the horizon becomes smaller. A little smaller, then smaller again, then smaller still. At first, the change is almost impossible to measure. Later, it becomes undeniable. This shrinking horizon raises one of the deepest questions in theoretical physics. What happens to the information trapped within? Earlier we discussed the information paradox. Every star swallowed, every planet consumed, every particle crossing the event horizon. All of that information appears trapped. Now the container itself is shrinking. The vault is becoming smaller. Eventually the vault will disappear entirely. The closer physicists examine this scenario, the stranger it becomes. Imagine a library containing every book ever written. Now imagine the library gradually shrinking while somehow preserving everything inside. Eventually the building becomes tiny, yet the information remains. How is that possible? Black holes force physicists to confront questions very much like that. As evaporation proceeds, the problem becomes increasingly urgent. The universe cannot postpone the issue forever. Sooner or later, the black hole's mass approaches smaller and smaller values. Sooner or later, the remaining storage space becomes limited. Sooner or later, the final stages arrive. Interestingly, those final stages occupy only a tiny fraction of the black hole's total life. This is true for many processes in nature. Most of the waiting happens early. The dramatic changes happen late. Consider an avalanche. Snow accumulates slowly. Pressure builds gradually. The final collapse happens quickly. Black holes display a similar pattern. Most of existence passes in near stability. The ending accelerates. A supermassive black hole may spend almost all of its life looking nearly unchanged. Then, comparatively speaking, the final transformation arrives with surprising speed. Of course, speed remains a relative term here. We're still discussing enormous intervals, yet compared to the earlier phases, events begin unfolding much faster. Mass loss increases, temperature rises more rapidly, radiation intensifies. The giant is no longer merely fading, it is actively unraveling. If observers existed to watch this process, they would witness something extraordinary. One of the most durable objects in existence would finally begin looking vulnerable. For countless ages, black holes appeared invincible. Stars died around them, galaxies evolved around them, the universe itself aged around them, yet they endured. Now the balance shifts. The black hole becomes the changing object. The thing that once outlasted everything else now finds itself moving toward its own conclusion. There is something almost ironic about that. The object famous for swallowing stars eventually becomes one of the last major sources of energy in the cosmos. The object associated with darkness gradually becomes brighter. The object once regarded as eternal begins revealing its mortality, and still the process continues. The radiation grows stronger, the mass falls lower, the horizon shrinks further, the feedback loop tightens, aging becomes acceleration, acceleration becomes transformation. Transformation becomes inevitability. Eventually, after surviving for durations beyond ordinary comprehension, the black hole reaches a stage unlike anything that came before. The slow fade gives way to something much more dramatic. The temperature rises to extraordinary levels. The remaining mass drops rapidly. The ancient giant approaches a moment that physicists have debated for decades. By the standards of the universe, black holes are masters of patience. They spend ages beyond imagination doing almost nothing that an outside observer would notice. They quietly collect matter. They quietly bend space-time. They quietly leak tiny amounts of Hawking radiation into the darkness. For most of their existence, they appear stable, permanent, unchanging. If you had somehow watched a supermassive black hole for 1 billion years, you probably wouldn't have seen anything remarkable happen. Watch it for 1 trillion years, and the story would not be very different. Watch it for trillions upon trillions upon trillions of years, and only then would the slow leak begin to reveal itself. Yet every story that has a beginning eventually reaches an ending. Even the longest-lived objects in existence are no exception. And that brings us to one of the most dramatic questions in all of theoretical physics. What happens during the final moments of a black hole's life? Does it simply fade away? Does it quietly disappear? Or does it go out with an explosion? The answer is surprisingly complicated, partly because nobody has ever witnessed a black hole reaching its end, partly because no black hole in today's universe is anywhere close to that stage, and partly because the final fraction of a second pushes our theories to their limits. To understand why, let's return to a process we've discussed several times already: the feedback loop. Throughout most of a black hole's life, Hawking radiation is extraordinarily weak. A giant black hole loses mass slowly. Very slowly. So slowly that the process seems almost irrelevant. But Hawking radiation contains a strange twist. As mass decreases, temperature increases. As temperature increases, radiation increases. As radiation increases, mass decreases faster. The process feeds itself. Imagine a block of ice sitting in the sunlight. Normally the ice melts. As it becomes smaller, there's less ice remaining. The process eventually slows because there is less material available. Black holes behave differently. Their evaporation accelerates. The smaller they become, the faster they lose mass. The faster they lose mass, the hotter they become. The hotter they become, the more radiation they emit. For most of their existence, this acceleration is too small to notice. Near the end, it becomes impossible to ignore. Let's imagine a black hole that has already survived through the black hole era. The stars are gone. Galaxies have faded into distant memory. The universe has become dark and sparse. For unimaginable ages, the black hole has been evaporating. Its mass has steadily declined. Its temperature has steadily increased. Eventually, it reaches a stage where the process becomes dramatically different from everything that came before. At this point, the black hole is no longer a supermassive giant. It is no longer a stellar mass object. It has become much smaller, much hotter, much more energetic. The Hawking radiation pouring from it is no longer negligible. Instead, it becomes one of the brightest things left in its region of the universe. This is one of the great ironies of black hole physics. The darkest objects in existence eventually become increasingly luminous. Not because they suddenly start swallowing matter, not because they ignite nuclear fusion, because they are running out of mass. The closer they move toward death, the brighter they become. Think about a campfire. At the beginning, there is plenty of fuel. The fire burns steadily. As the fuel decreases, the fire weakens. Black holes reverse this intuition. The closer they move toward the end, the more energetic the process becomes. The final stages are not gentle. They are intense. A shrinking black hole eventually becomes hot enough to emit increasingly energetic particles. Not just photons, not just low-energy radiation, potentially entire showers of elementary particles, electrons, positrons, neutrinos, and many others. The dying black hole effectively converts its remaining mass into radiation. Tiny amounts at first, larger amounts later, then increasingly rapid bursts as the end approaches. Does it explode? The short answer is probably yes, but the details matter. When most people hear the word explosion, they imagine something like a supernova, a star suddenly blasting its outer layers into space, an enormous shockwave expanding outward, a brilliant flash visible across vast distances. The final moments of a black hole would be different. There is no atmosphere to blast away, no outer shell waiting to be ejected, no accumulated pressure suddenly breaking free. Instead, the black hole itself is disappearing. Mass is being converted into energy. The remaining reservoir is being emptied, and as the reservoir shrinks, the rate of energy release climbs dramatically. According to many calculations, the final moments should produce an intense burst of radiation, a sudden release of the black hole's remaining energy. In that sense, the ending resembles an explosion, not because something inside detonates, because the evaporation process accelerates to extraordinary levels. Imagine draining a giant reservoir through a pipe. At first, the flow is slow. Then the pipe somehow grows wider and wider. The water leaves faster and faster. Eventually, the remaining contents rush out in a final torrent. That image is closer to what physicists imagine. The black hole doesn't blow apart from within. The evaporation itself becomes the event. The leak becomes a flood. The flood becomes the ending. Exactly what that ending looks like remains uncertain, and this is where the story becomes especially interesting. The reason for the uncertainty is simple. Our best theories begin running into trouble near the very end. Throughout most of a black hole's life, physicists can use established equations. General relativity describes gravity. Quantum mechanics describes particle behavior. The calculations work remarkably well. Near the final moments, however, the black hole becomes extremely small, extremely energetic. The scales involved become extraordinarily tiny. And that's where one of the biggest problems in modern physics emerges. We still do not possess a complete theory of quantum gravity. In other words, we do not yet know exactly how gravity behaves at the smallest possible scales. General relativity works beautifully for large objects. Quantum mechanics works beautifully for tiny particles. Combining them remains one of the great unfinished projects in science. The final moments of a black hole sit directly at that intersection, the place where both theories become equally important. As a result, physicists can confidently describe much of the evaporation process. The very last instant remains more mysterious. Several possibilities have been proposed. One possibility is the straightforward evaporation picture. The black hole continues shrinking. The radiation grows stronger. The remaining mass converts into energy. A final burst occurs. The black hole disappears completely, simple, elegant, and consistent with many current calculations. Another possibility is that the evaporation process changes near the end. Perhaps new quantum effects appear. Perhaps the final burst differs from our expectations. Perhaps the black hole leaves behind something small, some kind of remnant. A tiny leftover object preserving information from the original black hole. These ideas remain speculative. Physicists continue debating them. The difficulty is that we cannot test the final moments directly. Every known black hole is far too large, far too young, far too far from the end of its life. Even the smallest naturally occurring black holes we know about would survive for periods that dwarf the current age of the universe. The ending remains a prediction rather than an observation. That doesn't mean the prediction is weak. Many aspects of black hole physics have been tested indirectly. Theoretical calculations have survived decades of scrutiny. Yet the final second remains one of the most extreme environments physics has ever attempted to describe. And extreme environments often contain surprises. There is another reason physicists care so much about the ending. The final burst may hold clues about the information paradox. Earlier we discussed a troubling question. What happens to everything that falls into a black hole? The stars, the planets, the radiation, the information. If the black hole completely disappears, something must account for all of it. Some researchers believe the answer lies within the Hawking radiation itself. Perhaps information slowly escapes throughout the evaporation process. Others suspect the final stages may play a crucial role. Perhaps information is released in ways we do not yet fully understand. Perhaps the ending reveals something profound about the nature of reality itself. This is one reason black hole evaporation attracts so much attention. The death of a black hole is not merely an astrophysical event. It may be a window into deeper laws of nature, a clue pointing toward the long-sought union of quantum mechanics and gravity. There is also a remarkable symmetry hidden within the story. A black hole begins its life through collapse. Matter falls inward. Space-time contracts. Gravity dominates. Gravity. The ending reverses that trend. Energy flows outward. Mass disappears. The object shrinks. What began through accumulation ends through dispersal. The giant collector becomes a source. The ultimate absorber becomes an emitter. The cosmic prison gradually dismantles itself. And after all the unimaginable ages we've discussed, after the rise and fall of stars, after the fading of galaxies, after the long darkness of the black hole era, the ending arrives astonishingly quickly. Not quickly by human standards, quickly relative to the rest of the black hole's life. A lifespan measured in numbers containing dozens or even hundreds of zeros concludes in a comparatively brief final act. The giant that once seemed eternal finally runs out of time. Its temperature soars, its radiation intensifies, its remaining mass dwindles. Then comes the last burst, the last release of energy, the last trace of an object that may have survived longer than almost anything else in the universe. And once that moment passes, another question immediately emerges. Perhaps the deepest question of all. If the black hole is gone, where did everything it consumed go? Back in the 1970s, when Stephen Hawking first revealed that black holes could slowly evaporate, many physicists were astonished. Not because the mathematics looked obviously wrong, not because the calculations contained an error. The shock came from a much deeper place. The new theory seemed to break one of the most important rules in all of physics. At first glance, the problem sounds surprisingly simple. Imagine throwing a book into a black hole. Not a valuable book, not a rare manuscript, just an ordinary paperback. The black hole swallows it. The book disappears behind the event horizon. From the outside, nobody can read its pages anymore. Nobody can recover its words. Nobody can examine its contents. The information appears lost. That seems unfortunate, but perhaps not particularly alarming. After all, lots of things become inaccessible. If you drop your house keys into the middle of the ocean, recovering them becomes extremely difficult. Yet physics draws an important distinction between difficult to recover and destroyed forever. And that distinction lies at the heart of one of the greatest mysteries in modern science. To understand why, we first need to talk about information. The word information sounds ordinary. We encounter it every day. Books contain information. Computers contain information. Conversations contain information. Yet physicists mean something slightly different when they use the term. In physics, information describes the complete state of a system. The positions of particles, their energies, their momenta, their quantum properties, everything necessary to fully describe what exists. Imagine a deck of cards. The arrangement of those cards contains information. Shuffle the deck, and the information changes. Burn the deck, and the cards disappear. Yet according to the laws of physics, the information itself is not necessarily destroyed. The smoke contains information. The ash contains information. The escaping heat contains information. The molecules spreading through the room contain information. Recovering the original deck would be practically impossible. But in principle, the information still exists. It has merely become scrambled. Nature appears remarkably protective of information. Again and again, physical theories suggest that information can be transformed. It can be hidden. It can be scattered. It can become extraordinarily difficult to reconstruct. Yet it does not truly vanish. This idea is deeply embedded within quantum mechanics. In fact, many physicists consider information conservation to be one of the most fundamental principles in reality. Then black holes arrived and complicated everything. Let's return to our book. Suppose the book falls into a black hole. The black hole grows slightly heavier. Its event horizon expands slightly. From the outside, those are the only visible changes. The words disappear. The pages disappear. The ink disappears. Every detail vanishes behind the horizon. For decades, many scientists accepted this situation without much concern. The information still existed. It was simply trapped inside the black hole, hidden, inaccessible, locked away. The black hole functioned like the ultimate cosmic vault. Then Hawking radiation changed the story. Suddenly, black holes were no longer eternal. Suddenly, they could evaporate. Suddenly, the vault itself could disappear. And that created a serious problem. Imagine storing every document on Earth inside a giant safe. The information remains secure. No issue. Now imagine the safe slowly evaporates until nothing remains. Where did the documents go? That's essentially the question physicists found themselves asking. A black hole forms. Matter falls in. Information accumulates. The black hole evaporates. The black hole disappears. What happens next? Where does everything go? At first, Hawking's calculations seemed to suggest an uncomfortable answer. Nowhere. The information appeared lost forever. The radiation escaping from the black hole looked random, thermal, featureless. It seemed incapable of carrying detailed information about everything that had fallen inside. Whether the black hole swallowed a star, a planet, a library, or an entire civilization appeared irrelevant. The outgoing radiation looked the same. That conclusion alarmed physicists. Not because they particularly cared about recovering lost books from black holes, because it threatened a foundational principle of quantum mechanics. If information can genuinely disappear, many cherished assumptions about physics become questionable. Imagine playing chess. The rules are carefully defined. Now imagine discovering that one rule occasionally vanishes without explanation. Suddenly the entire game becomes unstable. The information paradox created a similar feeling. Something fundamental seemed wrong. Either Hawking's calculations were incomplete, or quantum mechanics was incomplete, or our understanding of black holes was incomplete. Possibly all three. The mystery became known as the black hole information paradox, and despite decades of work, it remains one of the most famous problems in theoretical physics. The fascinating thing is that nobody doubts the paradox is important. Some of the brightest minds in modern science have devoted enormous effort to solving it. Entire careers have been built around the question. Yet the answer remains elusive. Over the years, physicists proposed numerous solutions. Some proved more successful than others. Let's explore a few of the most influential ideas. One possibility suggests that information never truly enters the black hole in the way we originally imagined. Instead, it somehow remains encoded on the event horizon itself. This concept emerged from an astonishing realization about black holes. Researchers discovered that a black hole's entropy appears proportional to the area of its event horizon, not its volume, its surface area. That result was deeply surprising. Normally we expect information storage capacity to scale with volume. A larger box holds more information than a smaller box because it contains more space. Black holes seemed different. The mathematics hinted that information might somehow reside on the surface. This eventually contributed to one of the most famous ideas in modern theoretical physics, the holographic principle. The name sounds futuristic, but the core idea is relatively simple. A hologram is a two-dimensional surface capable of encoding three-dimensional information. Similarly, some physicists propose that information about everything inside a black hole may be encoded on its boundary. The event horizon becomes a kind of cosmic storage device, not a physical wall. Not a hard surface, a deeper informational structure. If this picture is correct, information never truly disappears behind the horizon. Instead, it remains recorded in ways we do not normally perceive. And if Hawking radiation interacts with that stored information, perhaps the information can gradually escape. This possibility became increasingly attractive as researchers explored the problem further. Yet it introduced new challenges. How exactly does the information escape? How is it encoded within the radiation? How does the process preserve quantum mechanics? The details remain extraordinarily difficult. Another proposal suggests that Hawking radiation itself carries the information away. Not obviously, not directly, not in a form that would be easy to recognize. Imagine shredding an encyclopedia, then scattering the pieces across an entire continent. The information still exists. Recovering it would be unbelievably difficult. Some physicists suspect Hawking radiation behaves similarly. The outgoing particles may appear random, yet hidden correlations could preserve the information. The details become distributed throughout the radiation itself. Over immense spans of time, the black hole slowly returns what it consumed, not as books, not as planets, not as stars, as information encoded within quantum patterns. If true, the black hole ultimately functions less like a destroyer and more like an unimaginably complicated recycler. Everything returns eventually, just not in the form anyone would recognize. There is another possibility, one that many physicists find less satisfying but still worth considering. Perhaps tiny remnants survive after evaporation ends. Instead of disappearing completely, the black hole leaves behind an extremely small object. This remnant stores the information indefinitely. The paradox disappears because the information never actually leaves existence. The challenge is that such remnants create their own difficulties. How could something incredibly small store enormous amounts of information? How would the physics work? Could infinitely many states fit inside a tiny remnant? The idea remains controversial. Some researchers find it plausible, others remain skeptical. Then there are even stranger suggestions. Certain speculative models propose that information escapes into newly created regions of space-time. Some involve baby universes, others involve quantum tunnels. Still others suggest that our understanding of space and time themselves requires revision. One reason the information paradox remains unsolved is that it touches multiple areas of physics simultaneously: gravity, quantum mechanics, thermodynamics, information theory, cosmology. All of them intersect here. The paradox sits precisely at the place where our best theories overlap. And unfortunately, overlap is often where contradictions become visible. Perhaps the most remarkable aspect of the problem is that it transformed how physicists think about black holes. Originally, black holes were viewed primarily as gravitational objects, massive things with strong gravity, simple, elegant, interesting. The information paradox revealed something deeper. Black holes are also informational objects. Questions about data, memory, encoding, storage, and retrieval suddenly became central to black hole physics. The field evolved dramatically. Researchers who once focused mainly on gravity began studying information. Quantum entanglement became increasingly important. New mathematical tools emerged. Entire branches of theoretical physics grew around the puzzle. In a strange way, the information paradox may prove more valuable than the solution itself. Many scientific breakthroughs occur because a problem forces people to think differently. The paradox has already generated profound insights into quantum gravity. Even if the final answer remains elusive, the journey toward that answer has transformed modern physics. Let's return one final time to our original question. Where does everything a black hole consumed go? The honest answer is that we do not know with complete certainty. We know the information cannot simply be ignored. We know Hawking radiation changes the story. We know black holes eventually disappear. We strongly suspect that information survives in some form, but the precise mechanism remains one of the great unfinished mysteries of science. That uncertainty is not a weakness. It is a reminder that physics remains an active exploration. Even today, there are questions about reality that nobody has fully solved. The information paradox is one of them. Somewhere within its solution may lie clues about quantum gravity itself, clues about space, time, entropy, and perhaps even the ultimate structure of the universe. Because once we begin asking where the information goes, another question naturally follows. What if a black hole doesn't disappear entirely? What if, after all the evaporation and all the radiation and all the unimaginable ages of decline, something remains behind. Among all the questions raised by dying black holes, this one may be the most stubborn. Not because physicists have ignored it, quite the opposite. For decades, researchers have examined it from every conceivable angle, hoping to determine whether the evaporation process truly ends with complete disappearance or whether something survives. At first glance, the answer seems obvious. If a black hole loses mass through Hawking radiation, and if that process continues long enough, eventually there should be no mass left, no event horizon, no black hole, nothing remains. Simple, clean, finished. Yet physics has a way of becoming complicated whenever we push it to its limits. And the final moments of a black hole happen very close to those limits. As we discussed previously, Hawking radiation becomes stronger as a black hole becomes smaller. The shrinking process accelerates, the temperature rises, the energy output increases, everything appears to point toward complete evaporation. The problem is that our current theories become increasingly uncertain as the black hole approaches extremely small sizes. Throughout most of a black hole's life, physicists can comfortably use established equations. General relativity handles gravity, quantum mechanics handles particles. The calculations produce sensible results. Near the end, however, the situation becomes far more difficult. The black hole shrinks towards scales where both gravity and quantum effects become equally important. This is precisely the region where our understanding remains incomplete. We still do not possess a fully successful theory of quantum gravity. And because we lack that theory, we cannot say with absolute confidence what happens during the final stages. This uncertainty leaves room for an intriguing possibility. Perhaps a black hole does not vanish completely. Perhaps something survives. The idea sounds almost like a loophole. After all, we've spent much of this story discussing evaporation. We've watched the black hole shrink. We've followed it through unimaginable ages. We've seen it approach its final moments. Now we're suddenly asking whether the ending actually ends. Yet the question is taken seriously by many physicists. The surviving object, if it exists, is usually called a remnant. The name is appropriately modest. No grand title, no dramatic label. Simply a remnant, a leftover, a tiny survivor from one of the most extreme processes in the universe. To understand why remnants became attractive, we need to revisit the information paradox. The paradox arises because information appears trapped inside the black hole. Stars fall in, planets fall in, radiation falls in, information accumulates, then the black hole evaporates. If the black hole completely disappears, what happens to everything it once contained? One possible answer is that the information gradually escapes through Hawking radiation. Many physicists currently favour some version of that idea. Another possibility is that the information remains stored inside a remnant. The black hole shrinks. The event horizon disappears. Most of the mass evaporates. Yet a tiny object survives. The information remains preserved within it. Problem solved, at least in principle. The appeal of this idea is obvious. Information is not destroyed. Quantum mechanics remains safe. The paradox disappears. The universe avoids breaking one of its most cherished rules. Unfortunately, the solution introduces a new problem, actually several new problems. The biggest difficulty concerns storage capacity. Imagine compressing an entire library into a grain of sand. That would be impressive. Now imagine compressing every library on Earth into a grain of sand. Far more difficult. Now imagine storing the information from an entire star, or an entire solar system, or billions of years of accumulated matter. The challenge becomes extraordinary. A black hole remnant would presumably be very small, perhaps incredibly small. Yet it would need to store potentially enormous amounts of information. How is that possible? Physicists have debated this issue for decades. Some theories suggest that the storage capacity of remnants could be far greater than intuition suggests. Others argue that such objects would create serious inconsistencies within quantum theory. the discussion remains unresolved. Another concern involves stability. Suppose remnants exist. Why would they remain stable? What prevents them from decaying further? Why does evaporation stop? Remember, Hawking radiation originates from quantum processes near the event horizon. As the black hole shrinks, the radiation intensifies. What mechanism suddenly halts the process? A successful remnant theory must answer that question. Several proposals attempt to do so. Some involve quantum effects becoming dominant at extremely small scales. Others suggest that space-time itself behaves differently than we currently expect. Still, others propose entirely new physical principles. The difficulty is that we cannot directly test these ideas. The scales involved are simply too extreme. A fascinating aspect of the remnant hypothesis is that it transforms the black hole's ending from a disappearance into a transformation. The black hole does not die in the traditional sense. It changes form. Most of its mass vanishes. Most of its energy escapes. Yet a tiny core survives. Like the ember remaining after a fire, like the seed remaining after a fruit. The original object is gone, but something remains. Whether nature actually works this way is another matter. Many physicists remain skeptical, not because remnants are impossible, because they create theoretical complications. Yet the idea refuses to disappear, and that persistence tells us something important. The final stages of black hole evaporation remain genuinely mysterious. Whenever multiple competing explanations survive for decades, it usually means science has reached the edge of current understanding. Black holes have pushed us to that edge repeatedly. Interestingly, remnants are not the strangest possibility researchers have proposed. Far from it. Some theories venture into territory that sounds almost unbelievable. One such idea involves baby universes. The concept emerges from certain speculative approaches to quantum gravity. The basic picture goes something like this. Instead of simply storing information or releasing it through radiation, a black hole might create a new region of space-time, a separate universe, a tiny offshoot branching away from our own. Matter falls into the black hole. Information enters the new region. The black hole eventually disappears from our perspective, yet the information survives elsewhere. It's an astonishing idea, the sort of idea that sounds more at home in science fiction than theoretical physics. And to be clear, there is currently no direct evidence supporting it. Nevertheless, serious researchers have explored versions of this possibility. The reason is simple. When existing theories become incomplete, physicists investigate alternatives. Sometimes those alternatives turn out to be wrong. Occasionally they reveal entirely new ways of understanding reality. Baby universes belong to that category. Speculative, unproven, yet intriguing enough to study. Another proposal involves quantum tunnels. Quantum mechanics allows particles to perform behaviors that would appear impossible in classical physics. Under certain circumstances, particles can effectively tunnel through barriers. Some researchers have wondered whether similar processes might influence black hole evaporation. Perhaps information escapes through mechanisms we do not yet fully understand. Perhaps the final stages involve pathways hidden from current theories. Again, these ideas remain highly speculative, but they illustrate an important point. The death of a black hole may not be as straightforward as it first appears. The closer physicists look, the more possibilities emerge. There is another reason scientists hesitate to declare complete evaporation the final answer. History teaches caution. Again and again, nature has revealed unexpected layers beneath apparently simple phenomena. Atoms once seemed fundamental. Then subatomic particles were discovered. Planets once appeared to move in perfect circles. Then more accurate models emerged. Even black holes themselves evolved from mathematical curiosities into real astrophysical objects. When a problem survives for decades, researchers learn humility. The universe often turns out to be stranger than expected. That doesn't mean every speculative idea is correct. Far from it. Most will probably prove wrong. Yet the existence of uncertainty itself is significant. It tells us the story is unfinished. Suppose for a moment that remnants do exist. What would they be like? The honest answer is that nobody knows. They would almost certainly be extraordinarily small, possibly approaching the Planck scale, the regime where quantum gravity becomes important. They might possess unusual quantum properties. They might interact weakly with the rest of the universe. They might persist indefinitely, or they might survive only under specific conditions. The possibilities are numerous because the underlying physics remains unclear. One particularly interesting consequence concerns the future universe. If every black hole leaves behind a remnant, then the far future of the cosmos contains more than radiation. It contains a population of tiny survivors, ancient relics carrying information from long-vanished stars, planets, and galaxies. The universe would not become entirely empty. Fragments of its history would remain scattered throughout space, invisible archives preserving records of earlier ages. Whether those archives could ever be accessed is another question entirely. Most likely not. But the information would still exist, and that possibility continues to attract attention because it offers a potential resolution to one of physics' deepest puzzles. At the same time, many researchers believe the information paradox will ultimately be solved without remnants. Perhaps Hawking radiation already contains everything necessary. Perhaps information slowly escapes throughout the evaporation process. Perhaps the event horizon itself behaves in ways we do not yet fully understand. Recent developments in quantum information theory have strengthened this perspective, yet even those advances have not completely eliminated alternative ideas. The debate continues. That's one of the fascinating aspects of modern theoretical physics. Not every important question has an answer, at least not yet. Sometimes scientists spend decades narrowing possibilities, refining theories, and testing assumptions before a solution finally emerges. Black hole evaporation belongs firmly in that category. We understand vastly more today than we did 50 years ago, and still, fundamental mysteries remain. So can a black hole leave something behind? Perhaps. The possibility remains open. Remnants may exist. They may not. The information may escape entirely through Hawking radiation, or nature may employ a mechanism nobody has yet discovered. What makes the question so compelling is that it sits at the crossroads of several profound mysteries: gravity, quantum mechanics, information. Space-time itself. Where those ideas meet, certainty becomes difficult, and uncertainty becomes valuable, because every unresolved question points toward new discoveries waiting beyond our current horizon. As remarkable as remnants may be, however, they raise an even larger question. Suppose black holes disappear completely. Suppose no remnant survives. Suppose the evaporation process truly reaches its conclusion. What happens when the very last black hole in the entire universe finally dies? There comes a point in this story where even enormous numbers begin to feel small. That sounds impossible at first. After all, we've already travelled through timescales measured in trillions upon trillions of years. We've watched stars disappear. We've watched galaxies grow old. We've watched black holes inherit the universe and slowly begin spending the mass they accumulated across cosmic history. Surely, there can't be much left after that. Yet the death of the final black hole lies even farther ahead, much farther. In fact, if the history of humanity were represented by a single heartbeat, and the entire age of stars occupied a single day, the black hole era would still stretch onward for a period so vast that those earlier intervals would seem surprisingly brief by comparison. This is one of the strangest consequences of Hawking radiation. The largest black holes do not merely outlive stars, they outlive almost everything. For unimaginable ages, they remain the dominant surviving structures in the cosmos. They are the last great monuments of an aging universe, and eventually, one by one, they disappear. The smaller black holes vanish first, then larger ones, then larger still. The process unfolds over intervals so immense that words like future begin to lose their ordinary meaning. The universe enters a period where almost every significant event involves black holes evaporating. One ancient giant fades away, then another, then another. Each disappearance marks the end of an object that may have survived longer than entire eras of cosmic history. Yet no matter how large a black hole is, the outcome remains the same. The leak never stops, the mass never stops decreasing, the countdown never stops advancing. Eventually the population dwindles. The universe becomes increasingly empty, increasingly quiet, increasingly dark, until finally only a handful remain. This is where the story becomes especially fascinating. Imagine observing the cosmos during this final phase. Not from Earth, of course. Earth is gone, the Sun is gone, the Milky Way as we know it is gone. Everything familiar vanished long ago, yet somewhere in this unimaginably distant future, a few remaining black holes still endure. They are ancient beyond comprehension, older than any star that ever lived, older than any galaxy in its original form, older than structures that once seemed permanent. These survivors represent the final members of their kind, the last giants, the last collectors, the last remnants of an earlier universe, and they are dying, one after another. For most of their existence, black holes evaporate incredibly slowly. Near the end, the process accelerates. Temperature rises, radiation increases, mass disappears more rapidly. What once looked eternal begins moving toward conclusion. Now imagine the final black hole. Not merely the final black hole in a galaxy, not the final black hole in a cluster of galaxies, the final black hole anywhere, the last one remaining in the observable universe. Its existence alone would be extraordinary. Every other black hole would already be gone. Every stellar remnant that could disappear would have disappeared. The cosmos would have spent ages shedding structure, yet this final object would still remain, a lone survivor drifting through a universe that has become almost unimaginably empty. At this stage, emptiness takes on a meaning very different from what we experience today. Modern space is not truly empty. Interstellar space contains gas, dust, radiation, particles. Even the vast voids between galaxies contain traces of matter and energy. The far future becomes emptier than that, much emptier. The expansion of the universe continues throughout these ages. Distances keep growing. Regions of space become increasingly isolated. The remaining particles spread farther apart. Encounters become rare, then rarer still. The universe gradually approaches a state where finding anything becomes difficult. Imagine standing in a desert. Then imagine making the desert larger, then larger again, then removing almost everything from it. That's closer to the environment surrounding the final black hole. The universe becomes a place of enormous distances and very little activity. Against this backdrop, the last black hole slowly evaporates, its temperature rises, its radiation strengthens, its remaining mass decreases. The process that began trillions upon trillions upon trillions of years earlier approaches its conclusion. There is something almost symbolic about that moment. For much of cosmic history, black holes represented endings. Stars ended as black holes. Matter disappeared into black holes. Light vanished into black holes. They were destinations, final chapters. Now the final black hole itself approaches an ending. The destination reaches its own destination. The collector becomes something collected by time itself. And still the evaporation continues, particle after particle, photon after photon. The remaining mass steadily converts into radiation. One of the remarkable features of this scenario is that the final black hole becomes increasingly energetic as it shrinks. Earlier in its life it was cold, very cold. Near the end it becomes hot, very hot. The radiation intensifies dramatically. The object that once seemed completely dark gradually becomes one of the brightest things remaining in the universe. Not because it is gaining energy, because it is losing it. The final reservoir is being emptied. The last account is being closed. The last chapter is approaching its final page. Eventually, the remaining mass becomes extremely small. The black hole enters a regime where our theories become uncertain. General relativity and quantum mechanics both become important. Quantum gravity likely plays a central role. Exactly what happens next remains one of the major unanswered questions in theoretical physics. Yet most scenarios share a common theme. The black hole does not survive indefinitely. The evaporation continues. The remaining mass disappears. A final burst of energy occurs, and then the black hole is gone. Completely gone. No event horizon, no gravitational prison, no dark sphere hiding in the depths of space. Nothing. The last black hole has died. Black hole. For the first time since black holes first appeared in the universe, there are none remaining. That statement sounds simple. Its implications are enormous. Think about everything black holes represented throughout cosmic history. They were engines of galaxy formation. They shaped stellar evolution. They influenced the growth of structure. They served as repositories of matter and information. For unimaginable ages, they dominated the future cosmos. Now they are absent. The universe has crossed a threshold. An entire category of object has vanished. Forever, at least according to current theory. What remains afterward? Surprisingly little. The answer depends somewhat on which physical theories prove correct. Yet the broad picture remains remarkably consistent. After the final black hole dies, the universe becomes extraordinarily sparse. Radiation remains, particles remain, perhaps dark matter remains, perhaps some remnants of earlier processes survive. But the great structures of cosmic history are gone. No stars, no galaxies, no black holes, no stellar nurseries, no luminous skies. The cosmos enters an age unlike anything that came before. One way to think about it is through architecture. Imagine a vast city. At first it is filled with activity. People move through the streets. Buildings are constructed. Lights shine from every window. Over time the population declines. Structures age. Neighborhoods empty. Eventually only a few major buildings remain. Then those disappear too. What remains is not destruction in the dramatic sense. It is absence. The framework itself has faded. The universe experiences something similar. The final black hole's death does not trigger a catastrophe. No universal shockwave races across existence. No grand cosmic collapse occurs. The event is significant because of what it represents. A transition, a boundary, the ending of one era and the beginning of another. In many ways, the death of the last black hole marks the conclusion of the universe's age of structure. Throughout cosmic history, matter organized itself into increasingly complex forms. Stars, planets, galaxies, black holes. Now even the longest-lived structures have disappeared. The cosmos becomes simpler, more uniform, more diffuse. There is a certain irony here. The objects once regarded as the ultimate survivors eventually join everything else. Nothing receives a permanent exemption. Not stars, not galaxies, not black holes. The universe appears remarkably committed to change. Given enough time, every familiar structure yields, every monument falls, every giant fades. The final black hole merely happens to be the last giant standing. Its death does not end the universe. That's an important distinction. The universe continues existing afterward. Space remains, time continues, particles and radiation persist. Reality itself does not switch off. Instead, the cosmos enters an even stranger phase. A phase where the absence of black holes becomes one of its defining characteristics. If the last black hole has vanished, what does the universe actually look like then? What remains to fill the darkness? What survives when stars are gone, galaxies are gone, and even the great black holes have finally disappeared? Darkness is a concept that sounds simple until you spend enough time thinking about it. Most of us experience darkness every day. We turn off a lamp. The sun sets. Clouds block the light. We step into a room with no windows. Darkness, in ordinary life, usually means the absence of illumination. Something that was shining is no longer shining. Something that was visible becomes difficult to see. Simple enough. Yet when physicists imagine the universe after the last black hole has disappeared, they encounter a strange problem. The future cosmos may become so empty that even the word darkness starts losing its usual meaning. Because darkness implies the existence of something that could have been illuminated, and in this unimaginably distant future, there may be very little left at all. The journey to that point has already been extraordinarily long. Stars have died, galaxies have changed beyond recognition, black holes have inherited the universe, black holes have evaporated, the final giant has vanished. Now the cosmos enters a new age, not an age of stars, not an age of black holes, not even an age of galaxies. Something quieter, something simpler, something far more difficult for the human mind to picture. One reason this future feels so strange is that our intuition depends heavily on structure. Look around any room and you'll see objects, walls, furniture, books, screens, people. Even when we step outside and gaze at the night sky, we still encounter structure. Stars cluster into galaxies. Galaxies gather into larger cosmic networks. The universe feels organized, not perfectly organized, certainly, but structured. The future after the last black hole is very different. By this point, most of the great structures that once defined cosmic history are gone. The large concentrations of matter have disappeared. The bright sources of radiation have vanished. The universe becomes increasingly uniform, increasingly sparse, increasingly difficult to distinguish from one region to another. Imagine standing on a vast plain that stretches forever in every direction. No mountains, no rivers, no trees, no buildings, just endless flatness. Now remove almost everything from that plain. Make it larger, then larger again. That still falls short of describing the future cosmos. The reason is that space itself continues expanding. This expansion has been occurring throughout the entire story we've been following. Even today, distant galaxies move farther apart as the universe grows. The process does not stop when stars die. It does not stop when black holes evaporate. It continues. Year after year, trillion after trillion years, the distances separating surviving particles become enormous, then more enormous, then larger still. The future universe does not merely become empty, it becomes stretched. Imagine drawing two dots on a rubber sheet. Now stretch the sheet. The dots move farther apart. Stretch it again. They separate further. Repeat this process endlessly. That gives some sense of what cosmic expansion accomplishes over unimaginable timescales. The remaining contents of the universe become increasingly isolated. If observers somehow existed during this era, they would find themselves living in a remarkably lonely cosmos. Not lonely in an emotional sense, lonely in a physical sense. The nearest particles might be separated by extraordinary distances. Interactions become rare, then rarer, then almost non-existent. This is where the idea of darkness becomes interesting. Today, darkness exists because light sources are absent. At night, the stars remain. The moon remains. Distant galaxies remain. Even the darkest sky still contains enormous amounts of radiation. The future universe may contain so little structure that darkness itself ceases to be the primary feature. Emptiness becomes the defining characteristic. The distinction is subtle but important. Imagine entering a dark warehouse. The lights are off. You cannot see much, yet the warehouse still exists. Shelves remain. Walls remain. Objects remain. The darkness hides structure. The far future universe contains far less structure to hide. The emptiness is genuine. There are several reasons physicists think the cosmos may evolve this way. One involves entropy. Earlier in our journey, we discussed the tendency of entropy to increase. Systems naturally move towards states with greater disorder. A dropped glass shatters, a hot cup of tea cools, a tidy room becomes messy unless someone actively maintains it. The universe follows the same principle on enormous scales. Entropy grows. Energy spreads out. Differences become smoothed away. The future after the last black hole represents entropy operating across the largest possible scales. Matter becomes distributed. Energy becomes diluted. Structure gradually disappears. The universe approaches a state where meaningful differences become increasingly rare. This scenario is often associated with a concept called heat death. Despite the dramatic name, heat death is not an explosion. It is not destruction. It is not a sudden ending. Heat death describes a condition in which usable energy becomes unavailable. Energy still exists. The problem is that it becomes evenly distributed. Imagine placing a hot object beside a cold object. Energy flows. Work can be performed. Interesting things happen. Now imagine both objects reach exactly the same temperature. The energy remains. Yet useful processes stop. The difference that drove change has vanished. The future universe may experience something similar. Energy remains present, but opportunities for meaningful transformation become increasingly scarce. This is one reason the era after black holes is so difficult to imagine. Almost every process we associate with activity depends on differences. Temperature differences, pressure differences, density differences. The future cosmos smooths those differences away. As it does, activity declines. Now, there is an important caveat. Physicists do not know every detail of the far future. Several uncertainties remain. One major uncertainty involves protons. Protons are among the building blocks of ordinary matter. Atoms contain them. Planets contain them. People contain them. Almost everything familiar depends on them. Some theories suggest protons may eventually decay. If true, ordinary matter itself gradually disappears over immense timescales. The process would be extraordinarily slow. No proton decay has ever been observed, yet many theoretical models predict it. If those models are correct, the future universe becomes even emptier. Matter itself slowly dissolves. The remaining particles drift apart. The cosmos grows increasingly sparse. Another uncertainty involves dark matter. Today, dark matter appears to constitute much of the universe's mass. Yet we still do not know exactly what dark matter is. Its future remains unclear. Perhaps it survives indefinitely. Perhaps it decays. Perhaps it participates in processes not yet understood. Different possibilities produce different futures. What remains consistent across most scenarios is the overall trend. The universe becomes less structured, less crowded, less active. And that brings us back to the title of this section, A Universe Without Darkness. At first, the phrase sounds contradictory. Surely an empty future cosmos would be the darkest environment imaginable. Yet darkness requires contrast. Darkness requires the possibility of light. Darkness requires something to illuminate. In the far future, there may be so little structure remaining that darkness becomes an inadequate description. The universe no longer resembles a dark room. It resembles something closer to a nearly featureless expanse. The distinction may seem philosophical, but it reflects a genuine physical difference. A dark forest remains full of trees. A dark city remains full of buildings. A dark galaxy remains full of stars hidden from view. The future cosmos contains progressively fewer things altogether. There is another fascinating consequence of this emptiness. Time itself may begin feeling different, not because the laws of physics change, because meaningful events become extraordinarily rare. Human beings measure time through change. Days pass because Earth rotates. Years pass because Earth orbits the Sun. Ages pass because civilizations rise and fall. The future universe offers fewer and fewer markers. Long intervals may pass with almost nothing occurring. If an observer somehow existed, measuring the passage of time could become a profoundly different experience. Events that once happened constantly become rare, then rarer, then almost absent. The universe settles into a kind of cosmic stillness, not perfect stillness. Quantum processes continue, particles remain, space-time persists. Yet the grand activity that once defined cosmic history is largely over. One of the remarkable things about modern cosmology is that it allows us to think about futures this distant at all. No human will witness them. No telescope will observe them directly. Yet by following the implications of known physics, scientists can sketch possible outlines of these remote eras. The resulting picture is both strange and surprisingly coherent. The universe begins hot and dense. Structure emerges. Stars form. Galaxies grow. Black holes appear. Black holes dominate. Black holes disappear. The cosmos becomes increasingly empty. The story unfolds naturally from the same physical laws operating today. Of course, surprises remain possible. History teaches us humility. Every generation believes it understands more than previous generations. Then new discoveries arrive. Perhaps future physics will reveal processes we have not imagined. Perhaps entirely new structures emerge. Perhaps quantum gravity introduces unexpected behavior. The far future remains uncertain in many details, yet even uncertainty carries lessons. The fate of the universe reminds us that permanence is remarkably difficult to find. Stars seem permanent. They are not. Galaxies seem permanent. They are not. Black holes seem permanent. They are not. Again and again, nature reveals that change operates across every scale. The timescales differ, the mechanisms differ, the outcomes differ. But the principle remains surprisingly consistent. Everything evolves, everything transforms, everything participates in a larger story. And after the final black hole disappears and the universe settles into its sparse future, one last question remains waiting. Perhaps the biggest question of all. After all the evaporation, after all the fading, after all the unimaginable ages of cosmic evolution, can we really say that a black hole is gone? Or does something deeper survive? After spending so much time talking about black holes, it is tempting to think we already know the answer. A black hole forms, it grows, it consumes matter, it slowly evaporates. Eventually it disappears, case closed, the black hole dies. Yet the closer physicists examine the problem, the less straightforward that conclusion becomes, because the word die carries assumptions. It suggests an ending, a disappearance, a point beyond which nothing remains. For many things, that definition works perfectly well. A candle burns out, the flame vanishes, the candle's life is over, a star exhausts its fuel, its nuclear furnace shuts down. The star changes into something else. Its previous life has ended. Black holes seem as though they should fit into the same category. After all, we've spent this entire journey following their decline. We've watched Hawking radiation slowly carry energy away. We've watched temperatures rise. We've watched masses shrink. We've watched giant black holes fade across timescales so enormous that entire eras of the universe passed by like brief moments. Eventually the event horizon disappears. The black hole vanishes. Surely that's death. And yet one question refuses to go away. What happened to everything that was inside? That question sits at the center of modern black hole physics. It appears again and again. Every path through the subject eventually circles back to it. The information paradox, the fate of Hawking radiation, the possibility of remnants, the structure of space-time, the nature of quantum gravity, all of them lead back to the same mystery. If a black hole truly dies, what becomes of the information it once contained? Imagine taking every book ever written, every photograph, every recording, every memory preserved in digital form. Then imagine compressing all of that information into a single vault. For billions of years, the vault remains sealed. Nothing escapes. Nobody can access its contents. Then one day, the vault disappears completely. Would you say the information died? Or would you first ask where it went? That is essentially the question physicists ask about black holes. And increasingly, many researchers suspect the answer is that information never truly dies at all. The details remain controversial, the mathematics remains difficult. Yet over the past several decades, a remarkable shift has occurred. When Hawking first introduced black hole evaporation, many scientists believed information might genuinely be lost. Today, the majority of theoretical physicists lean toward a different conclusion. They suspect information survives, somehow, somewhere, in some form. The challenge is understanding exactly how. One reason this issue became so important is that quantum mechanics appears unusually protective of information. Again and again, quantum theory suggests that information can become scrambled beyond recognition. It can become scattered. It can become hidden. But it does not simply vanish. Think about a jigsaw puzzle. Suppose you throw all the pieces into the air. The puzzle is ruined. The image is lost. The pieces land everywhere. Yet the information required to reconstruct the picture still exists. The arrangement has become chaotic. The information has not ceased to exist. Many physicists suspect black holes behave similarly. The information becomes unimaginably scrambled, perhaps distributed throughout Hawking radiation, perhaps encoded in subtle quantum relationships, perhaps preserved through mechanisms we do not yet fully understand, but not destroyed. If that view is correct, the death of a black hole begins looking less like annihilation and more like transformation. The black hole disappears, the information remains, something ends, something survives, and that distinction changes everything. Because once information enters the discussion, black holes stop being merely astronomical objects. They become windows into the deepest foundations of reality. In fact, some researchers now believe black holes may be teaching us something profound about space and time themselves. Let's explore one of the most surprising developments in modern theoretical physics, the holographic principle. Earlier, we briefly mentioned the idea. Now, let's look at why it matters. The holographic principle emerged from attempts to understand black hole entropy. Researchers discovered something deeply strange. The information associated with a black hole appears related to the area of its event horizon, not its volume, its surface. This result seemed almost absurd at first. Imagine buying a hard drive. You naturally expect its storage capacity to depend on how much space exists inside it. A larger volume should hold more information. Black holes appeared to be operating according to a different rule. The information seemed connected to the boundary itself. That realization eventually inspired a radical possibility. Perhaps the universe works this way too. Perhaps the three-dimensional world we experience emerges from information encoded on lower-dimensional boundaries. The idea remains mathematically complex, yet its implications are extraordinary. If correct, black holes are not merely objects within the universe. They may reveal something fundamental about how reality itself is constructed. The death of a black hole would then become more than an astrophysical event. It would become a clue about the architecture of existence. That possibility helps explain why black hole research attracts such intense interest. On the surface, black holes seem remote. Most people will never encounter one. Most exist thousands or millions of light years away. Yet the questions they raise strike at the heart of physics. What is information? What is space? What is time? How does gravity relate to quantum mechanics? Why does the universe behave the way it does? These questions remain unresolved, and black holes sit directly at the crossroads. Another fascinating aspect of the problem involves the event horizon itself. For many years, physicists treated the event horizon almost like a passive boundary, a point of no return, a simple dividing line. modern research increasingly suggests the situation may be more complicated. Some proposals describe the horizon as an active participant in information storage. Others suggest quantum effects create structures that classical physics never predicted. Ideas such as firewalls, soft hair, and quantum extremal surfaces have entered the discussion. The names sometimes sound whimsical. The mathematics behind them is anything but. Each proposal attempts to answer the same question. How does information survive? The fact that so many ideas exist tells us something important. The mystery remains open. Science has not yet delivered a final verdict, and that's perfectly normal. Many of history's greatest scientific problems require decades or centuries to solve. The nature of planetary motion, the structure of atoms, the origin of light, the evolution of life. Each seemed mysterious until new insights arrived. Black holes may simply represent the current frontier. Future generations of physicists may eventually regard today's debates the way we regard older scientific controversies. Important steps toward a deeper understanding. There is another perspective worth considering. Suppose for a moment that information truly survives. Suppose Hawking radiation eventually returns every detail, every particle, every interaction, every fragment of history. What would that mean? Oddly enough, it would mean that black holes are not perfect destroyers at all. They are extraordinary transformers. A star falls in, a planet falls in, radiation falls in, the original objects disappear. Yet the information persists in altered form. The black hole becomes less like a shredder and more like a cosmic blender. The ingredients are no longer recognizable, yet nothing fundamental has been lost. This idea aligns surprisingly well with broader themes in physics. Again and again, nature seems to favor transformation over destruction. Energy changes form. Matter changes form. Stars become remnants. Remnants become black holes. Black holes become radiation. The universe constantly rearranges itself. Perhaps information participates in the same pattern. Perhaps nothing truly disappears. Perhaps everything merely changes. Of course, caution is necessary. We should distinguish between poetic interpretations and scientific conclusions. Physics does not currently prove that nothing is ever lost. The information paradox remains an active area of research. Important details remain unresolved. Quantum gravity remains incomplete. Yet the direction of modern thinking is striking. Many of the most promising ideas point toward preservation rather than erasure, and if they are correct, the death of a black hole becomes surprisingly difficult to define. What exactly has died? The event horizon? Yes. The black hole as a recognizable object? Certainly. The gravitational prison? Absolutely. But the information? Perhaps not. The deeper contents? Perhaps not. The physical history encoded within the system? Perhaps not. The more closely we examine the problem, the more the word death begins feeling inadequate. Maybe a black hole dies the way a wave dies when it reaches a shore. The visible structure disappears. Yet the water remains. Maybe it dies the way a cloud dies when it dissolves into the atmosphere. The shape vanishes. The substance continues. Or maybe the truth is stranger than any comparison we can currently imagine. That possibility should not be underestimated. The history of science contains many examples where reality proved more surprising than the intuition. Black holes themselves were once regarded as mathematical curiosities. Today they are central players in astrophysics. Quantum mechanics once seemed impossible. Today it underlies modern technology. Future discoveries may reveal aspects of black hole death that nobody has yet anticipated. And that brings us back to the question that started this journey. What really happens when a black hole dies? The most honest answer is both simple and complicated. We know black holes are not eternal. We know Hawking radiation slowly removes their mass. We know they shrink. We know they grow hotter. We know they eventually reach a final stage. We know the event horizon disappears. We know the black hole, as an object, comes to an end. Those conclusions are among the most remarkable achievements of modern theoretical physics. Yet the deeper story remains unfinished. What happens to the information? How does quantum gravity behave during the final moments? Do remnants survive? Does Hawking radiation preserve everything? Does the universe encode information in ways we have only begun to understand? Those questions remain open, and perhaps that is the most fitting ending possible. We began this journey with an object that seemed eternal. We discovered that it is not. We followed its life across timescales beyond imagination. We watched it inherit the future universe. We watched it fade. We watched it approach extinction. And just when it seemed the mystery was solved, another mystery appeared beneath it. The black hole dies. The questions survive. And somewhere in those questions may lie the next great breakthrough in our understanding of reality itself.